Hey, what's going on, everybody? It's your bro, hope you're doing well, and in this video we're going to discuss data structures and algorithms. So sit back, relax, and enjoy the show. If you wouldn't mind, please like, comment, and subscribe. One like equals one prayer for the YouTube algorithm. Here's a few of the topics that we're going to cover in this series. First, we will learn about basic data structures, followed by big O notation, then searching algorithms, sorting algorithms, graphs, and trees. Be sure to look for the timestamps in this video's description. Well, what's a data structure? Simply put, a data structure is a named location that can be used to store and organize data. Here's a real-life example. Think of a family tree. It's a hierarchy of family relationships. We need some way to organize all of this data. A tree is a data structure. What about arrays? We have a little bit of experience with those. An array is a collection of elements stored at contiguous memory locations. That's another example of a data structure. It's basically a named location that can be used to store and organize data. Different data structures store and organize data in different ways. Each of them has their own pros and cons. Well, what's an algorithm? An algorithm is a collection of steps to solve a problem. It's the steps to a solution. Here's an example. I'm hungry and I need a pizza. That's my problem. An algorithm to bake a pizza could be 1. Heat the oven, 2. Knead the dough, 3. Add the toppings, and then eventually you'll solve your problem of not being hungry anymore. So that's a real-life example of an algorithm. One algorithm that you're probably familiar with is a linear search. Suppose we have an array of elements and I need to find a value. Using a linear search, we would, one by one, examine the elements of an array to find a value. A linear search is an example of a searching algorithm. I know what you're probably thinking. Why do I need to learn data structures and algorithms? What's the point? Well, let me tell you. You'll write code that is both time and memory efficient. And 2 commonly asked questions involve data structures and algorithms in coding job interviews. Do you know how to reverse a doubly linked list? No, you don't, do you? So you should probably watch this series. So without further ado, ladies and gentlemen, let's begin. Hey, what's going on, everybody? It's your bro, hope you're doing well. In this video, I'm going to explain the stack data structure, so sit back, relax, and enjoy the show. Alright, everybody, stacks. A stack is a LIFO data structure. LIFO is an acronym for last in, first out. This allows us to store objects into a sort of vertical tower, like a stack of books or a stack of CDs. We use the push method to add objects to the top of the stack, and the pop method to remove objects from the top. So here's a real-life example of us creating a stack data structure. After declaring our stack, we can add objects to our stack. The objects that we'll be adding are various video games. To add an object to our stack, we use the push method, like we're pushing something onto our stack. So let's push Minecraft onto the bottom of our stack. And then next, we'll add Skyrim, then maybe some Doom, then Borderlands, and then Final Fantasy VII. So this is a LIFO data structure, last in, first out. To access objects on the bottom of our stack, we first need to pop or remove objects from the top of our stack. If I need to access Minecraft on the bottom, I don't want to pull this from the bottom because everything on the top is going to fall, right? So that's kind of the concept. So in order to access Minecraft on the bottom, I need to pop or remove objects from the top in order to access objects on the bottom. So in order to access Minecraft, I need to remove all the games on the top of my stack. So that's kind of the point of a stack data structure. Now let's create a stack. The language you use really doesn't matter for the most part. You can implement a stack in Java, Python, C++, C#. The language really doesn't matter. However, the syntax might be slightly different. I just so happen to be using Java, so I'll stick with that. Now to push objects onto our stack, we first need to declare our stack and instantiate it. So let's do that. Stack. Then we will list the data type of the objects that we will be adding to our stack. Luckily, strings are a type of object, and they're fairly simple, so we will create a stack that can store strings, the names of video games. And I will name the stack stack to keep it simple. Stack equals new stack. And I will list the data type and then add a constructor. Okay, so we now have a stack data structure. Now with stacks, they have 5 unique methods. Let's take a look. Now with stacks, we can push an item onto the top of our stack, we can pop an item from the top of the stack, we can peek at the item at the top of the stack, we can check to see if our stack is empty, and we can search our stack for an item. So those are 5 unique methods available to stacks. Let's first check to see if our stack is empty. So let's use system.out.println stack.empty method. And currently our stack is empty. That is true, but that'll change soon. So let's push some games onto the top of our stack. So we type the name of our stack, and use the push method, then pass in our object. So we will pass in a string, the name of a video game. Let's add Minecraft first. Then let's add Skyrim. Then Doom. You can pick your own games if you want, I don't care. Then Borderlands. And then Final Fantasy VII. FFVII. Okay, let's check to see if our stack is empty now. So let's move this line of code to the bottom. And run it. So our stack is no longer empty. This returns false. So with the stack, we can at least take a look at the items within the stack without removing them. So let's use system.out.println and I will print my stack. So this will print all of the objects within my stack, beginning with Minecraft, then Skyrim, Doom, Borderlands, and Final Fantasy VII. However, by printing our stack, we're not removing items from the stack, so that's completely fine. So this time, let's pop the topmost item from our stack by using the pop method, stack.pop. And we don't need to list an object, because pop will always remove the topmost object from our stack. So now Final Fantasy will be missing from the top of our stack. So if I was to repeat this again, well then this will remove Borderlands, and then Doom, then Skyrim, and then lastly Minecraft. Then if you pop again, this is what happens. An exception, empty stack exception, so that's something to keep in mind. Now when you pop the topmost object from a stack, this will actually return that object. If you need the object from the top of the stack, you can pop it and then assign it to something. So let's say string my fave game equals stack.pop. And then I will print my fave game. And this will print Final Fantasy VII. And it should be missing from the top of my stack if I was to print my stack. So Final Fantasy VII is no longer in my stack because I popped it, then assigned it to the string variable of my favorite game. So in order to take the topmost object from a stack, you use pop and then assign it to something. If you ever need to take a look at what the topmost object is within your stack, you do not want to use pop because that will remove it. You can instead use the peek method of stacks. So what I'll do is system.out.println stack.peek. And then immediately follow this with printing my stack. So let's run this. So the topmost item within my stack after using the peek method is Final Fantasy VII. Then after printing my stack, Final Fantasy VII is still at the top of my stack. So if you ever need to take a look at the object that is at the top of the stack without removing it, you can simply use the peek method. If you need to search for an object within the stack, you can use the search method. Let's print stack.search, and we pass in our object as an argument. So the very first item in a stack will have a position of 1. You would think it's 0, but it's actually 1. Now let's find Borderlands. That will be in position 2 from the top. Then Doom would be, of course, 3. Skyrim is 4. Then Minecraft is 5. So if you search for an item that is not within the stack, like Fallout 76, well then this will return -1. If search does not find this object within your stack, it will return -1. So with stacks, we can actually run out of memory. So let's add like 1 billion copies of Fallout 76. We find Bethesda's warehouse of unsold Fallout 76 games. So we'll create a stack of 1 billion copies of Fallout 76. We can do this using a for loop. Int I equals 0, as long as I is less than like 1 billion. That's probably close enough. Increment I, then we will push a copy of Fallout 76 to our stack. So stack.push dot push Fallout 76. And this is what happens.
A few moments later.
So we will run into an out-of-memory error due to the Java heap space. So it is possible to run out of memory when adding objects to our stack. Now, this is an interesting feature that may or may not happen to you if you add a billion copies of Skyrim onto a stack. Damn it, Todd Howard, you did it again! Now, what are some uses of stacks? Here's a few examples. One, we can use them in undo, redo features in text editors, like when we go to edit, then undo typing, or redo typing. We can move back or forward through browser history by hitting the back or forward button in the top left corner of most web browsers. We can implement them in backtracking algorithms if we need to navigate a maze or search through file directories. And another is that we use them when calling functions. Whenever we call a function, we add what is known as a frame to the call stack, but I'll probably save this topic for another video. So in conclusion, everybody, a stack is a LIFO data structure, last in, first out. It stores objects into a sort of vertical tower, a stack of objects. You use the push method to add objects to the top, and the pop method to remove objects from the top. So those are stack data structures. In the next video, we'll be covering queues, which work a little bit different. So if you can, give this video a thumbs up and drop a random comment down below. But yeah, that is a stack data structure in, well, computer science. What's going on, everybody? It's your bro. Hope you're doing well. In this video, I'm going to explain queues in computer science. So sit back, relax, and enjoy the show. If you find this video helpful, please remember to like, comment, and subscribe. Your support will help keep this channel running. Whoa, hey, we're talking about queues today. So queues are a FIFO data structure, not to be confused with FIFA. FIFO as in first in, first out. An example would be a line of people. It's first come, first serve. Whoever's there first gets helped first. So this is a collection designed for holding elements prior to processing. It's a linear data structure. Here's an example. Imagine that we're a cashier and we're selling tickets to a concert. We will help whoever approaches our register first. It's first come, first serve. In other words, it's FIFO. First in, first out. Unfortunately, a wild Karen appears and she would like to talk to the manager. Now, Karen is going to waste everybody's time, so it's going to be a while. In the meantime, Chad enters the line. He will enter in at the back and wait his turn, followed by Steve and then Harold. So Karen is at the head of our queue, our line, and Harold is all the way at the back, our tail. As you can see, Harold is very anxious right now. Once Karen has been defeated, Chad will move to the head of our queue. So Chad will now be helped next, and Harold will still be at the tail until somebody else enters the line. Once Chad has been helped, he will move out of our queue, and Steve is at the head now, and the tail will move as well. And then once Steve has been helped, Harold is the only one currently waiting in line for his tickets. He will be at both the head and the tail of our queue. So that's kind of how a queue works. It's first come, first serve, FIFO, first in, first out. If you were here first, then you will be helped first. Now, the concepts of adding and removing objects from a queue are known as both enqueuing and dequeuing. Enqueuing is the concept of adding an object to the end of our queue, our tail, and dequeuing is when we remove an object from the head of our queue. Now, what methods do you need to enqueue and dequeue from a queue? Well, it really depends on the programming language that you're working with. A lot of you voted for data structures and algorithms using Java, so I'll probably stick with Java then. Here's an example. Now, to enqueue and dequeue, we need, well, a queue. So let's create one. Queue. Then we need to list the data type of the objects that we're going to add to this queue. Let's work with strings because strings are objects and they're fairly simple. And I will name this queue Q equals new. Now check this out. I will attempt to create a queue object and instantiate it, and the data type is string, and I will add a constructor. Now we cannot instantiate the type queue. Here's the reason why. So if we take a look at the queue class right here, queue is actually an interface and not a class, and based on our lesson on interfaces, we cannot create an instance of an interface. An interface is meant to be more of like a template that we can apply to another class. So to utilize queue technology, we need a class that implements queue. Now, taking a look at our Java collections hierarchy, there are two classes that implement queues. one of which is the linked list, and the other is the priority queue. Now, priority queues, they will rearrange their elements based on a certain priority, so they wouldn't be a good example. So to utilize the features of a queue, we are going to create a linked list because we cannot instantiate a queue itself because it's an interface. With that being said, let's change equals new queue to equals new linked list. We won't be focusing on any of the features of linked lists. We'll save that for another video, maybe the next one. I haven't decided yet. So we will only cover the features that linked lists will utilize via the queue interface. Now, with the queue interface, there are three methods that we inherit from the collection's parent class: add, remove, and element. These will do approximately the same thing as enqueuing, dequeuing, and peeking at the topmost element. However, they throw exceptions, and according to the documentation, it's actually better to use this column of methods instead. These will return a special value. We have offer, which will enqueue or add an element to the tail of our queue. Poll will dequeue. It will remove the head of our current queue. And then there is also peek. It will not remove the head, but it will examine it and return it. So those are the three dedicated methods that we implement via the queue interface. There are some additional methods too, which we'll cover later, which we inherit from the collections class. So let's begin by offering a bunch of people to our queue. This is how we enqueue or add elements to our queue. So first in our line, we have Karen. So to add her to the queue, we would type the name of our queue, queue.offer. And we will offer Karen to the front of our queue, and she would like to complain to the manager. Next, we have Chad, queue.offer Chad. Then we have Steve. And lastly, Harold. Okay, now if we were to display our queue, we'll place it within a printline statement. We will pass in queue as an argument, and this should display our queue in order. First, we have Karen at the head, then Chad, Steve, then Harold at the tail. One method that we implement from the queue interface is the peek method. We can use the peek method to examine and take a look at the object at the head of our queue. We're not actually going to remove the object at the head of the queue, but take a look at it. So within a printline statement, I will use queue.peek method. And after peeking over our cash register, unfortunately, Karen is at the front of the line. Now to dequeue, we can use the poll method. So type queue.poll. And this will dequeue your queue. So Karen is no longer at the head of our queue. So let's poll a couple more times for practice. So after polling twice, Karen and Chad are now gone. Using poll a third time, we'll remove Steve. And lastly, Harold. Now the nice thing about the poll method is that it will not cause an exception. According to the Java documentation, you can use element to peek, but it will throw an exception. So if I was to use element at the end, this would cause an exception then. So usually it's preferable to use this column of methods, even though they're similar. These will not throw exceptions: offer, poll, and peek. Now with queues, there are some additional methods that you might be interested in. The queue class will extend the collection class, so the queue class inherits everything that the collection class has. And there's some pretty useful methods within here. I'll show you a few. So the first is that we can check to see if our queue is empty. So within a printline statement, I will type queue.isEmpty. And if our queue is empty, this will return true. So if I move this line of code after we offer a bunch of strings, a bunch of people to our queue, if we check to see if our queue is empty, that will be false. There are people currently within our line. So that is the isEmpty method. We can also check to see the size of our queue. How long is our line? System.out.println queue.size. And the size of our line, our queue, is 4 objects. We have 4 people waiting in line to be helped. So that is the size method. And another is the contains method. We can check to see if our queue has a certain object that we're looking for. So within a printline statement, I will type queue.contains and then pass in an object. Let's check to see if Harold is at the back of the line. He's been waiting here patiently. q.contains Harold. And according to the contains method, Harold is in fact within our line. That is true. However, this method does not give the index the position in which Harold is in. Imagine that we yell out, "Hey, Harold, are you there?" And he yells back, "Yeah," or "True." That's kind of how the contains method works. So these are three useful methods that queues inherit from the collection class. Now, where could queues be useful? They're actually used in quite a number of things, but here's a few examples that came to mind. So one, they can be used in keyboard buffers. Have you ever typed so fast that the computer couldn't render all of the characters onto the screen, and all of those characters were added to a buffer? They were all displayed in sequence, and they were waiting for their turn to be displayed. So with a keyboard buffer, letters should appear on the screen in the order that they're pressed, right? First in, first out. They're also used in printer queues. Print jobs should be completed in order, so we would start with page 1, then page 2, and just follow that pattern. And as we discussed before, they're used in linked lists, priority queues, as well as breadth first search algorithms. Well, everybody, in conclusion, a queue is a FIFO data structure. First in, first out. It's a collection designed for holding elements prior to some sort of processing. It's a linear data structure. Imagine a bunch of people waiting in line. To enqueue, that means to add an element to the tail of our queue to the end. We can use the offer method in Java. To dequeue, we would use the pull method in Java. That will remove the element at the head of our queue. So that is the queue data structure. In the comments down below, let me know what you would tell Karen if she asked to speak with your manager. And that, ladies and gentlemen, is the queue data structure in the field of computer science. Hey everybody, it's your bro, hope you're doing well, and in this video we're going to discuss priority queues in computer science. So sit back, relax, and enjoy the show. Hey, what's going on everybody? So priority queues. A priority queue is a FIFO data structure, first in, first out. However, a major difference with priority queues is that before we start polling and serving elements, we put them in some sort of order. Higher priority elements are served first, before elements with lower priority. So here's an example. Let's say that we have some student GPAs, and we'll place them all within a queue, and then a priority queue, and take a look at the differences. So let's create a queue. The data type is queue, and we are going to insert some doubles, some GPAs. I'll name this queue equals new. Now queues are actually interfaces, and we can't implement them directly, so we need to use a class that utilizes the queue interface. One that I know of is a LinkedList. Then finish instantiating it. Now to add data to a queue, we use the offer method. Queue.offer, and then pass in a GPA. Let's make sure that these are not in order. How about a 3.0? Then the next student has a, let's say, 2.5. Then a 4.0, 1.5, and 2.0. Okay, now let's display the elements of our queue. One easy way in which we can do that is to use a while loop. And this is our condition. We'll continue this while not logical operator queue dot is empty method. While our queue is not empty, pull each element and display it. So within a print line statement, let's use queue.pull to display and remove each element, beginning with the first one, and then working our way to the end. So this will display the elements within my queue. So these are in first come, first serve order. Whatever element we were offered first, we are serving that element first. If an element was added last, well then it's served last. So that's a standard queue. Now with a priority queue, we're going to arrange them in some sort of order before we actually pull these elements. So let's change our linked list to a priority queue. And run this again, and let's take a look at the differences. Okay, these are all in order now. So if we're working with numbers like doubles, these are arranged in ascending order, beginning with the smallest element. Let's pretend that these are grade point averages, GPAs. Why might we want to put these in order? Let's say whatever student performed the worst gets 2 hours of free tutoring, whichever student performed second worst gets 1 hour of free tutoring, and third gets half an hour of free tutoring. Now, if you need these in descending order, well, there's one change that we're going to make. Within the constructor, we can pass in a comparator, but that's a little advanced for us and we haven't discussed that yet. So there is a default comparator that we can use found within collections. Collections dot reverse order method. So these elements will be in reverse order then. In this example, let's say that whichever student has the best GPA will receive, I don't know, a gold medal, like the Olympics. And the second best student will receive a silver medal, then a bronze medal. And then every student after that, I guess, will receive nothing. But that's okay though, they got some free tutoring in the last example. Okay, now let's change the data type. Let's say that these are now strings. And let's put these in standard order. So let's change these to strings. Maybe this student has a B. This one has a C. A. F. And what are we missing? D. If we have a priority queue of strings, well then these elements will be in alphabetical order. So if we need these in reverse alphabetical order, again we can pass in a comparator, and then one that we can use is from collections. Collections dot reverse order. And these elements within our priority queue are now within reverse alphabetical order. So yeah, that's a priority queue. Think of it like a queue. However, we first sort these elements based on a certain priority. We will pull and serve the elements with the highest priorities first, and work our way to elements with lower priority. So yeah, that's a priority queue. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, those are priority queues in computer science. Hey, what's going on everybody? It's your bro, hope you're doing well. In this video, we're going to discuss linked lists in computer science. So sit back, relax, and enjoy the show. Now, before we dive straight into linked lists, we're going to take a closer examination of arrays and array lists. We will see what disadvantages that these data structures have, where linked lists excel at, so we'll compare and contrast the differences between the two. With what we understand with arrays and array lists, these data structures store elements in contiguous memory locations. In this demonstration, I'm storing letters of the alphabet. Suppose that the first element of my array has a memory address of 123 Fake Street. Obviously, these are not real memory addresses, but this is how I like to think about things. If this was a memory address, then the next element in my array may have an address of 125 Fake Street, then 127 Fake Street, 129 Fake Street, and then you just continue on in that pattern. Now, arrays are fantastic at randomly accessing elements because they have an index, but they're not so great at inserting or deleting elements, especially when those elements are closer to the beginning of the array. Here's an example. Suppose I need to insert a new element at index 3. Since this element is already occupied with a value, I would need to shift my elements to the right in order to accommodate room for this new element. So the process of shifting is cumbersome. But once this element is empty, then I can insert a new value. So it's not that big of a deal if I have a small data set, but imagine if I had 1 million elements. I would need to shift my data up to that many times depending on the location of the insertion. And the same concept applies with deletion as well. We would shift our elements to the left to close the gap. You're probably thinking, dude, why are you talking about arrays in a video about linked lists? Well, where arrays have difficulty inserting and deleting, linked lists actually have the advantage. Here's a representation of a linked list. A linked list is made up of a long chain of nodes. Each node contains two parts: some data that we need to store and an address to the next node in line, also referred to as a pointer. Linked lists do not have an index the same way that arrays do, but each node contains an address to where the next node is located. So these nodes are non-contiguous. They can really be anywhere within your computer's memory. If our initial node has a memory address of 123 Fake Street, like our array example, then the next node in our linked list could have a memory address of maybe 101 Help Boulevard, and another could be 404 Nowhere Lane, then 666 Crime Circle. Each node knows where the next node resides. I imagine this as if we're following a scavenger hunt or a series of clues to find the end of the linked list, the tail. Each node has an address, a clue as to where the next node is. We begin at the head and work our way towards the tail, following each clue, each memory address found in each node. Then we know when we reach the end of our linked list when we check that address, our pointer, and it has a value of null. That means we're at the tail, we're at the end of our linked list. Inserting a node is easy in a linked list. There's no shifting of elements involved. Wherever we need to place a new node, we take the address stored in the previous node and assign the address of our new node with the address from the previous node, so that our new node is pointing to the next node in line. Then we can take and replace the address in the previous node with an address that points to our new node. It's as simple as that, and we're completing our chain simply by inserting a node at a given location. There's only a few steps involved, no shifting of elements required. Deleting nodes are easy too. Wherever we need to delete a node, we have the previous node point instead to the next node in line. Again, no shifting of elements is necessary. Now, this is where linked lists tend to be inferior to arrays. They are bad at searching. We can randomly access an element of an array because we have an index. With a linked list, that is not the case. To locate an element, we need to begin at the head and work our way towards the tail until we find the element that we are looking for. This itself takes time. In fact, it would take linear time, but making the insertion or deletion of a node is constant. This variation of a linked list is a singly linked list. There are single links to each node. However, there's another variation called a doubly linked list. A doubly linked list requires even more memory to store 2 addresses in each node, not just one, which is the case with a singly linked list. One address for the next node and another for the previous node in our chain. The benefit of a doubly linked list is that we can traverse our doubly linked list from head to tail or from tail to head in reverse. Each node knows where the next and previous node is, but the downside is that a doubly linked list uses even more memory than a singly linked list. So how about we create a linked list in real life now? Let's do it. Alright, ladies and gentlemen, with all that out of the way, let's create a linked list. Linked list lists the data type of the objects we'll be storing within this linked list, just strings because they're easy, and I will name this linked list linked list. Linked list equals new linked list. And to list the data type again, we are storing strings, add a constructor, boom, you got yourself a linked list. Now, if I was to take my cursor and hover over my linked list declaration, there's a note here that says, this is a doubly linked list. Each node knows where the previous and next nodes are. Now, if we head to the linked list class itself, there's a few things I need to mention here. Our linked list stores the memory location of our first and last nodes. These are effectively the head and the tail of our linked list. And there's also an inner class named node. Each node knows the memory address of the next and previous nodes within this linked list. Now, taking a look at our linked list class definition, our linked list class implements the deck interface, and a deck is more or less a double-ended queue. So with the deck interface, we implement 12 additional methods. So here's just a few of them. So we can add to the head, add to the tail, remove the head, remove the tail, peek at the head, peek at the tail. Some will throw exceptions, some will return a special value, so you can use any combination of these really. And not only do we have these 12 methods, but we can treat our linked list as either a stack or a queue. We can push, we can pop, we can pull, and we can offer. So just to demonstrate, let's first treat our linked list as a stack. So linked lists do have a push method as well, if we need to push an element onto our linked list as if it were a stack. So let's push the letter A, and then I will display my linked list with a printline statement. System.out.println, linked list, and of course we have the letter A. So let's push another letter onto our stack. What about B? So at the bottom of our linked list we have A, and then on top we have B. Let's add a couple more letters. Let's represent a typical grading scale. We have C, D, and F. A, B, C, D, F. Notice that I'm intentionally leaving out E. We're going to insert that later. So within our linked list that's behaving as a stack, we have F on top, then D, C, B, and A. So we also have access to a pop method as well. Linked list.pop, and this will pop the top of my linked list. So F should no longer be here, it's D, C, B, and A. So we can treat a linked list as a stack. We can also treat it as a queue as well. And just to save some time, I'm going to copy these lines of code. To add an element to a queue, we do not use push, we use offer. So linked list.offer. And we will keep the order. So I'm not going to pop it quite yet. So we have A, B, C, D, F. A is at the head, F is at the tail. And to remove the head of our queue, we do not use pop, we use pull. And A is no longer in here, we have B, C, D, F. So you can use a linked list to mimic a stack or a queue. Before we move on to the next section, I'm going to get rid of this pull method. So we have a typical grading scale, A, B, C, D, F. Where linked lists are really good is the insertion and deletion of nodes. Let's say for this example, I need to add a node between D and F that contains the letter E. So that's really easy to do with a linked list. We would type the name of our linked list, dot add, list and index, like 4, and our object, E. And then to remove a node, we would type the name of our linked list, dot remove, then list the object, E. So E should no longer be within my linked list. So where linked lists tend to have an advantage over arrays and array lists is the insertion and deletion of nodes. However, there's one catch to this. With a linked list, we still need to traverse the entire linked list to find where we need to go. Unlike with arrays and array lists, there's no random access to a linked list. Searching for an element is fairly straightforward too. So within a printline statement, I'm going to use the index of method of a linked list. Linked list.index of, let's look for F. So that would be at index 4. And before we wrap things up here, here's a few methods related to linked lists that you might be interested in. We can peek at the head or the tail node of our linked list. So within a printline statement, I'm going to print linked list dot and then use the peek first method. So the first node within my linked list contains the letter A. So we can peek last as well. Linked list dot peek last. And the last node of my linked list contains the letter F. We can add new nodes at the head or the tail of our linked list by using the add first method for the head. So maybe I need to add maybe 0, because I don't really know what comes before A in the alphabet, so 0 would be a good bet, I guess. Or we could add to the tail by using add last. And after F comes G. And we now have G at the tail of our linked list. We can remove first and remove last. You can also store them within a variable too. Let's say string first equals linked list dot remove first. Then to remove the last node, we could just use remove last then. And let's store this within a different variable, remove last. So yeah, those are a few useful methods related to linked lists. In conclusion, everybody, a linked list is a data structure that stores a series of nodes. Each node contains 2 parts, some data and an address. Nodes are stored in non-consecutive memory locations. Each node can be really anywhere within your computer's memory, and elements are linked via these pointers. They contain an address for where the next node is. We've discussed 2 varieties of linked lists, a singly linked list as well as a doubly linked list. With a singly linked list, each node is made up of 2 parts, some data and an address. To traverse a singly linked list, we would begin at the head node and use the address as a sort of clue to find where the next node is located within our computer's memory. With a doubly linked list, each node is made up of 3 parts, some data and 2 addresses, one address for the next node and another address for the previous node, and it behaves the same way. And to traverse a doubly linked list, we could begin at the head and work our way towards the tail, or we could begin at the tail and work our way towards the head, depending on which way is closer to where we need to be within our linked list. What are some of the advantages of a linked list? 1, they're a dynamic data structure. They can allocate needed memory while our program is currently running. 2, insertion and deletion of nodes is really easy. If you're familiar with big O notation, this would be in constant time. There's only a few steps regardless of the size of our dataset. And 3, there is no to low memory waste. What are some disadvantages? 1, there is greater memory usage because we have to store an additional pointer. Each node also stores the address for where the next node is located, and even more so with a doubly linked list. This will use a lot more memory because we need 2 addresses for each node. Now 2, there's no random access of elements within a linked list. To find an element, we need to begin at one end and work our way towards the other end. And 3, accessing and searching of elements is more time consuming. This is done in linear time. This is where arrays and array lists have an advantage. Since they use indexing, they can randomly access an element of an array or an array list. With a linked list, we have to manually traverse the entire linked list to get to a particular index, since we don't have random access. Now, what are some uses of linked lists? 1, they could implement stacks or queues. If you need a stack or queue for anything, you could also use a linked list. 2, maybe GPS navigation. So let's say you have a starting position and a final destination. Each step or stop along the way is kind of like a node. And if you need to take a detour, you can easily change, insert, or delete a node and recalculate how to get to your final destination. 3. What about a music playlist? So each song within a playlist might not necessarily be next to each other within your computer's memory. You want your playlist to follow a certain order of songs. So that could be another use of a linked list. So those are linked lists. If you would like a copy of all my notes here and my code, I will post this to the comment section down below. If you can, give this video a thumbs up, drop a random comment down below, and well, yeah, those are linked lists. What the heck is a dynamic array? A dynamic array is an array with a resizable capacity. If we need extra room for elements, we can increase the capacity, which we cannot normally do with a standard, typical, fixed size array. Dynamic arrays are also known as ArrayLists in Java, vectors in C++, arrays in JavaScript, and lists in Python. Here's an example of a static array, and then we'll take a look at a dynamic array. A static array has a fixed capacity. We determine that capacity at compile time, and we can't change it later normally. In this example, I have a static array with a capacity of 6 elements and a size of 5 elements that are currently occupied. The last element is open, so it's null. Each element has a memory address. Obviously, these are not real memory addresses, but this is how I like to think about things. Imagine that all of these memory addresses are houses, and they're all next to each other. Now, accessing an element is easy because we have index numbers to work with. We can randomly access an element in O of 1 constant time. The size of our dataset doesn't matter. However, searching for a stored value still takes time because we need to begin at index 0 and iterate over our array until we reach our value, or the end in case we don't find it. This is done in O of n linear time. The larger the dataset, the time to finish will increase linearly. And in the case of inserting or deleting, that takes linear time unless done at the end. No shifting of elements is required. However, the closer we need to insert or delete to index 0, we need to shift all elements that follow in order to make room for insertion or close any gaps in the case of deletion. So if I need to insert a value at, let's say, index 0, I have to shift all elements to the right by 1 to make room for this insertion. And then we can insert a value. Now, currently with our static array, we're at capacity. Our array is full. Our size is equal to our capacity. Then in the case of deleting an element, we need to shift all elements that follow after this index where we're making the deletion and shift everything once to the left. So that would look like this. And our size is back to 5, so there is one element that is open. A major disadvantage of static arrays is that they have a fixed capacity. We can't increase the capacity once the size of the elements reaches capacity. In the separate example, I have an array with a capacity of 5 elements and a size of 5 elements, and it's completely full. I can't increase the capacity because the next memory block contains, I don't know, pictures of cats or something. You do you, I guess. A dynamic array has its own inner static array with a fixed size. Once the inner static array of our dynamic array reaches capacity, our dynamic array will declare and instantiate a new array with an increased capacity. Usually the amount that we increase the capacity by really varies depending on the programming language. It's usually between 1.5 and 2. I just picked capacity times 2 for extra emphasis. So what we'll do now is copy the elements over to our new array, and these have different memory addresses than our original array. So that would look something like this. We now have a new array with double the capacity, but like I said, it really depends on the language that you're working with. It's usually between 1.5 and 2. This array has a size of 5 elements that are full and a total capacity of 10. Then if you need to shrink the capacity, like if you're not using a lot of elements, you can always just do the reverse process of what we did to increase it. Now, with this new inner array, the insertion and deletion of elements is really the same as a static array. So you just shift all the elements to the right by 1 to insert a new element, or shift all the elements to the left to delete an element. What are some of the advantages of dynamic arrays? 1, there is random access of elements. That is done in O of 1 constant time. We can randomly access an element by an index number and retrieve the value. 2, there is good locality of reference and data cache utilization. Because all of these memory addresses are contiguous, they're right next to each other. Unlike with linked lists, you have to jump around a lot because all of the memory addresses are kind of random. And 3, it's easy to insert and delete elements at the end because there's no shifting of elements required. And for the disadvantages, a dynamic array wastes more memory than a linked list because we need to increase the capacity to accommodate more elements if we need the extra room. and we may not necessarily need all of this extra room, so a dynamic array wastes more memory than a linked list. 2. Shifting of elements is time-consuming. The closer we need to insert or delete, closer to index 0, we have to shift all elements that follow afterwards to the right in case of an insertion or to the left in case of a deletion. And 3. Expanding or shrinking the array is time-consuming because we have to copy all of the elements over to a new array with a different capacity. And that's the basics of dynamic arrays. Let's create our own dynamic array for practice. Alright, welcome back. We're going to create our own dynamic array using Java. In the future, if you ever do need a dynamic array, you might as well just use an array list. According to the description, it's a resizable array implementation of the list interface, and it's pre-built, so you might as well use it. I thought we would create our own dynamic array just for learning purposes and practice. But let's take a look at the ArrayList class. Within this class, there are a few defined members. There's a default capacity set to 10. There are overloaded constructors within this ArrayList class. We can set our own initial capacity, or we can use the default by not passing in an initial capacity. There is a size to keep track of how many elements are filled within our array list, and our array list does have its own inner static fixed size array. And if we ever need to expand the size of this array, we just copy the elements over to a new inner array. So let's begin. Let's create a new class named dynamic array, and I'll get rid of this. So file, new, class, and this will be named dynamic array. Then finish. Okay, let's declare a few members. Let's create int size, int capacity. This will be the initial capacity. I'll set this to 10, but feel free to pick whatever value that you want, as well as an array of objects named array. I will declare this, but not yet instantiate it. So you can make these private. However, I think that'll make our code a little more complex and difficult to understand, although it'd be more secure. I'm just going to use the default visibility for these members here. All right, let's create some overloaded constructors. So public dynamic array. And within here, we will instantiate a new fixed size array. This dot array equals new array of objects with a capacity of whatever capacity the default is. So it's going to be 10 by default. And we'll create an overloaded constructor just in case the user passes in their own capacity that they would like to set. So int capacity, this dot capacity equals whatever capacity that we pass in. Okay, let's instantiate a new dynamic array. Dynamic, make sure to spell it right, dynamic array, I'll call this dynamic array with a lowercase d equals new dynamic array. So I'm not going to pass in an initial capacity, and let's print whatever the capacity is of our dynamic array. Dynamic array dot capacity, and this should be 10. Okay, now let's pass in maybe a capacity of 5, and this should be 5. Yep, cool. So it seems like that works. All right, let's head back to our dynamic array and declare all of the methods that we'll need. Let's create an add method, public void add, and there will be one parameter of object data. Next method, insert, public void insert. The two parameters are int index object data. Okay, next method we have delete. Public void delete. There is one parameter of object data. Then we have search. Public int, we're going to return an index. Search. And we will need object data. And let's return -1 for now. Then we have private void grow to expand the size of our array. Private void shrink. Then we'll need an isEmpty method. Public, we will return a Boolean value, is empty. And we might as well fill this in right away because there's only one line. Return size is equal to 0. If our size is anything but 0, we will return false. And lastly, toString. Public string to string. And I need to type in something. I'm just going to return null for the time being until we return something. Okay, let's begin by filling in the add method. First, we'll want to check to see if we're at capacity. If our size is greater than or equal to our capacity, then we better call the grow method to expand the size of our array. So if there is room, we will take our array at index of size, that should be the end of our array, equals data. Then we will increase our size by 1. Now let's head all the way down to the toString method to display the elements of this array, and we just need to iterate over these. Let's declare a local variable of string, string, and I will set this equal to an empty string, and we will fill in the elements when we iterate over it. So let's iterate over the elements of our array. So let's create a for loop for int I equals 0, and then I will continue this for loop as long as I is less than our size. You can do capacity too if you want to see the entire array, but let's begin with size. I is less than size, and I will increment our index I by 1. So I'm going to take our string and append it. String plus equals our array at index of I, that's 1, I, plus maybe I'll add a comma, then a space. Then we should return our string. Okay, this isn't perfect yet, but let's at least test it. Let's head back to our main Java file and add a few elements to our array using the add method. So let's use the default capacity of 10, so we don't necessarily need to pass in anything. So to add to our array, we can use dynamic array dot, and we declared an add method at the top. So let's add maybe some letters. I will add the letter A, then B, then C. That should be good. So A, B, and C. And then let's call the toString method, system.out.println, and with the toString method, we only have to type in the name of what we would like to display the elements of. So dynamic array, and we don't necessarily need to type toString. So this should display A, B, and C. Now let's format this and clean it up a little bit. Like I would like to get rid of the last comma here, and maybe enclose all of these elements within a set of square brackets. So this is what we can do within the toString method. So after the for loop, let's check to see if our string does not equal an empty string. If that is the case, if there are elements to display, let's take our string. Then I'm going to create a substring and get rid of these last two characters, the comma and the space. So string equals string.substring, and the length is going to be beginning at index 0, and I will continue this until string.length method minus 2. Then after running this one more time, the comma and space at the end should no longer be there because we created a substring to end at the last element. Then let's enclose all of these elements within a set of square brackets. So I'll use some string concatenation. So I'll add a left square bracket, and then at the end add a right square bracket. And then these should be within square brackets now, and that looks a lot better. Now, what if our string is empty? Let's return just a set of square brackets using an else statement. Else, we will set our string equal to a set of square brackets, and that's it. So let's head back to our main Java file and comment these lines of code out where we add elements to our dynamic array. So let's run this, and we should have an empty set of square brackets. Actually, this would be a good opportunity to test our isEmpty method, so let's check that. So within a println statement, system.out.println, I will take my dynamic array and use the isEmpty method. Then I'm just going to use some string concatenation. Empty, colon, space, plus dynamic array isEmpty method. And our dynamic array is currently empty. That is true. Then let's fill this with elements A, B, and C. So this should iterate and display the elements of our array and let us know if our array is empty, which is false. Since we're here, let's display the size and the capacity of our array too. So system.out.println dynamic array dot size. And I'll use some string concatenation here too. So size colon space plus dynamic array dot size, and the capacity as well. So capacity plus dynamic array dot capacity. So this dynamic array has a size of 3 elements are filled in, and a capacity of 10. For fun, just to see the entire array, let's go to the toString method and change size to capacity, so we can see all of the elements that are filled in and not filled in. So after running this, we can see our entire array at its full capacity. So we have a size of 3 elements are filled in, but we have a total capacity of 10. The rest of the elements are null. So if we were to count all of these, they should be 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nice. So you can change that back to size, or you can keep it as capacity. I'll just keep it as capacity for teaching purposes. Now let's fill in the insert method. There's not a whole lot left to do. First, let's check to see if our size is greater than or equal to our capacity. If so, then we'll need to grow our array. So size is greater than or equal to our capacity. If that is the case, call the grow method. What we're going to do at this point is shift all of the elements that are filled in to the right in order to make room for the insertion. So let's use a for loop and iterate over our filled elements in reverse order. I will set int I, our index, equal to our size. And then I will continue this as long as I is less than our index. Then decrement I by 1. So I'm going to take our array at I and set this equal to array at index of I minus 1. This will shift all of the elements over to the right to make room for the insertion. So we will take our array at index equals whatever data we want to set, then increase our size by 1. So then if we head back to our main Java file, we can insert a value at a given index. So let's take our dynamic array dot use the insert method. Let's say at index 0, I would like to insert an x. So let's try it. Cool, we have x, a, b, c. The size is now 4 and the capacity is still 10. Now let's work on the delete method. Within here, we're going to iterate over the elements of our array beginning from left to right. So this is fairly easy. Int I equals 0. We will continue this as long as I is less than our size, and increment I by 1 after each iteration. So during each iteration, we will check to see if our array at index of I is equal to the data that we pass in as an argument. So if that is the case, we need to shift all of the elements to the left then. So we'll need a nested for loop for that. Then we will need an index of j because I is already taken. We're within a nested for loop. Int j equals 0, and I will continue this nested for loop as long as j is less than our size minus I minus 1. And then we are going to increment our index j by 1 during each iteration. So basically, wherever we make the deletion, we're going to shift all of the elements afterwards one spot to the left. So we will take our array at index of I plus j and set this equal to our array at index of I plus j, the same as before, but add plus 1. So that will target the next element that comes afterwards. So after we escape this for loop, we will take our array at index of size minus 1 and set this equal to null. And then we will decrement our size by 1. And actually, here would be a good place to shrink our array. So let's write an if statement and check to see if our size falls below a certain criteria. So let's say that if our size is less than or equal to a third of the capacity. So capacity divided by 3. We don't want to shrink too often just because that's time consuming. And then you may want to cast this as an int because it may not divide evenly. So if our size is underneath a third of the capacity, let's call the shrink method, and we will shrink our array by maybe half, but we'll get to that later. So then we want to break to escape this for loop then. Okay, let's try this then. So after making the insertion, let's delete, what about A? So dynamic array dot delete, and I do not need to pass in an index, just the data that I'm looking for. All right, so A is no longer in here. We have X, B, and C. The size is 3, and the capacity is still 10. All right, I promise we're almost finished. Let's fill in the search method next, and this one is fairly short. So we just need to iterate over the elements of our array beginning at index 0. For int I equals 0, I will continue this as long as I is less than the size of our array, increment I by 1. If our array at index of I is equal to the data that we're looking for, the data that we pass in as an argument, then we will return whatever I is, our index. If we do not find it, we return -1. That's kind of like a sentinel value. That means we did not find the value that we're looking for. Okay, so let's search for maybe C. Dynamic array dot search, and I will pass in the data that I'm looking for. I am looking for C, so that should be 0, 1, 2, assuming we insert and delete some values later. And then I'm going to place this within a print line statement. So dynamic array dot search, and I am searching for C. And our result is that C is at index 2, 0, 1, 2. All right, we're near the end. Let's grow and shrink our array, and I'll turn these lines into comments. Now, for the grow method, we're going to instantiate a new array, but we'll increase the capacity first. Int new capacity equals our old capacity, which is just named capacity. And let's say we want to increase the capacity by 2. And then I will just cast this as an int. Okay, so after we create a new capacity, we will instantiate a new array. Then we need to copy the elements over. So we'll have an array of objects named new array equals new array of objects with a capacity of our new capacity. And then we need to copy the elements over to our new array, and that's kind of time consuming but necessary. So we begin at index 0 for int I equals 0. We will continue this as long as I is less than our size. And I will increment this by 1 after each iteration. So we will take our new array at index of I and set this to our old array, just named array, at index of I. And then we will change the capacity to whatever new capacity is. Then lastly, we will set our array to equal our new array. Then let's test it. So I'm going to maybe add a bunch of elements. I'll keep that as a comment. So let's change the capacity of our array to 5. I'll pass in 5 into the constructor, so we have less elements to work with. So the size is 3 and the capacity is 5. I'm going to add another element. Let's try D. So size 4, capacity 5. Let's add E. Okay, so currently our array is full. Now let's try to increase the size past the capacity. So I will add F, and this should increase and grow the size of our array. So we have a capacity of 10 now, and we have a bunch of empty elements. And lastly, we just need to shrink this array. And this next part is super simple for the shrink method. Copy everything from the grow method and paste it within the shrink method, but change capacity times 2 to capacity divided by 2. Now we will call the shrink method automatically when the size falls below a third of the capacity. That means we have a lot of wasted memory. Now let's begin deleting elements. So I will type dynamic array.delete A, then maybe B. So when the size is a third of the capacity, that's when it should shrink. So we're not there yet. Let's delete maybe 1 or 2 more times. So let's delete C. And there we go. So the size is 3 and the capacity is now 5. Well, alright, that's a very basic dynamic array. If you're using Java instead of just building your own dynamic array, you might as well just use an array list because it's more efficient and, well, it's already coded for you. But I think this was good practice for us just to understand how dynamic arrays work. So if you would like a copy of all this code, of course, I will post this to the comment section down below. If you made it all the way to the end, please give this video a thumbs up, a random comment down below, And well, yeah, those are dynamic arrays and well, computer science. Hey, what's going on everybody? It's your bro, hope you're doing well, and in this video we're going to run some tests on both array lists and linked lists in Java, so sit back, relax, and enjoy the show. Alright, let's begin. We'll need both a linked list and an array list. So, linked list, the data type will be integers, and I will name this linked list equals new linked list. Again, the data type is integer, add a constructor, boom, we got ourselves a linked list. And now we'll need an array list. Change linked to array. This will be named array list. Make sure to pay attention to the capitalization. Equals new array list. And we'll need to keep track of the time. We'll need a start time, end time, and elapsed time. And these will be of the long data type. We'll be working with nanoseconds, so a long is preferable to an int. A long is really just a really long integer. Think of it that way. So we have start time, end time, and elapsed time. Okay, and now we'll need to populate both our linked list and our array list, and we can do that with a for loop. We'll need a large sample size, maybe 1 million elements. That'll be good. So int I equals 0. We'll continue this as long as I is less than a million, and I believe that's about a million. Yeah, we're good. Okay, then increment I by 1 during each iteration. So I'm going to add I to both my linked list and my array list. So we can add primitives because Java has an autoboxing feature. So even though these are integer objects, we can still add primitives. And be sure to add to our array list as well. So ArrayList.add I. Okay, let's move on. Now we'll keep track of the time. We'll need to assign the start time of value and end time of value before and after our operation. So let's say that start time equals, and we can get the current time of our JVM by using system.nanoTime method. And let's take a look. So this returns the current value of the running Java virtual machine's time source in nanoseconds. So we will get the start time after we do something. I'll just add a note here. Do something. Then we will get the end time. So end time equals system.nanotime method. And to calculate the elapsed time, that will be elapsed time equals end time minus start time. And then we'll probably want to display this, so let's do that. System.out.println, and let's say linked list, I'll add a tab too, plus elapsed time plus ns for nanoseconds. And let's just run this to test it. So this portion of code really took, right between here, took 400 nanoseconds. Okay, let's actually do something now. So let's get the first element within our linked list. Linked list.get 0. And let's see how long this takes. Okay, 13,200 nanoseconds. Now with an array list, let's copy everything that we have for our linked list and change linked list to array list. And be sure to do that here as well. Array list. And let's compare these. So we are getting the index of 0 for both our linked list and array list, and we will compare them. And it appears that our array list is slightly faster. Our linked list took 11,800 nanoseconds, and our array list took 6,700. So it looks like getting the first element of our linked list is going to be a little bit slower than our array list. This time, let's get something right in the middle of our linked list and array list. So I'm going to turn this line into a comment, and we will get the index of 500,000. So that's right in the middle. And do the same thing with array list as well. So array list dot get 500,000. And let's see how long this takes. Okay, so our linked list took way longer than our array list. Our linked list took 7.5 million nanoseconds compared to our array list's 6,900 nanoseconds. Okay, so that's still way longer with a linked list. Now let's try something near the end of our linked list and array list. What about the last element? Linked list dot get 999,999. So that is the last index in our linked list and array list. We have 1 million elements, and this is exclusive. And the first element has an index of 0. So let's do the same thing with ArrayList. ArrayList.get 999,999. And here are the results. Our linked list took 63,000 nanoseconds compared to our ArrayList's 17,000. Now, the reason that our linked list took less time to retrieve and index at the end is because this linked list is a doubly linked list, so we can begin at the head and work our way towards the tail, or begin at the tail and work our way backwards to the head. So since this index is right at the end, it's actually going to be very easy to retrieve this index, whereas in the middle is actually going to be the worst possible spot for a linked list, because we can start at either end, but it's still going to take the same amount of time to get to the middle. So it appears that accessing an element from an array list is always faster than a linked list, and that's to be expected because with an array list we have random access of elements. Unlike with a linked list, we have to begin at one end of our linked list and traverse our linked list until we get to the index that we're looking for. Now let's add or remove an element from our linked list and array list. Maybe just remove, because it's going to take really the same amount of time. So linked list dot remove. And let's remove the first element, so index 0, and do the same thing with array list. Array list dot remove index 0. And let's take a look again. Okay, so it appears that our linked list was actually faster this time. 17,000 nanoseconds compared to 2.2 million nanoseconds of an array list. And the reason that our array list took longer is because we need to shift all elements to the left after removing an element. So we had to shift 1 million elements after removing the first element. Now let's remove something near the middle. So let's remove index number 500,000. So linked list dot remove 500,000, and do the same thing with array list. Be sure to comment this line out. Array list dot remove 500,000. And here are the results. So it looks like our linked list took a lot longer this time, 7 million nanoseconds compared to 1.6 million nanoseconds for an array list. So with our array list, there were less elements to shift this time because we were right in the middle. But with our linked list, we still had to navigate to the middle to remove one of these elements. And then let's remove the element at the end of both our linked list and our array list. Linked list.remove 999,999, and do the same thing with array list. Array list.remove 999,999. And this time, our linked list is just slightly slower than our array list. Adding or removing elements near the end of an array list is actually fairly easy. The closer that we insert or delete near the end, the less time it's going to take because we have to shift less elements. And with a linked list, well, this is a doubly linked list, so accessing the last element doesn't really take too long. If it's near the middle, it's going to take forever, actually. So it seems that in most situations, an array list is going to be better than a linked list. However, if you have to do a lot of inserting or deleting, especially if it's a large data set, a linked list might be better, but it seems that an array list is going to be more flexible for most applications. So that is linked lists versus array lists. If you would like a copy of all of this code, I will post this to the comment section down below. And well, yeah, that's linked lists versus array lists in computer science. Hey, what's going on, everybody? It's your bro, hope you're doing well, and in this video I'm going to describe the very basics of big O notation in, well, computer science. So sit back, relax, and enjoy the show. Oh yeah, big O notation. So a common phrase used with big O notation is, how code slows as data grows. It describes the performance of an algorithm as the amount of data increases. And really, this notation is machine independent. What we're really focusing on is the number of steps to complete an algorithm, because some machines are going to run certain algorithms faster than others. And 3, we tend to ignore smaller operations. If we had some task that took n plus 1, we would just reduce it to just n because that plus 1 really isn't going to make a difference. So here's a few examples of big O notation. We have O of 1, O of n, O of log n, and O of n squared. And n is really just the amount of data that we're passing in. It's a variable like x. What we're focusing on is the performance of an algorithm as the amount of data increases, and n is a representation of the amount of data that we're passing in. Here's a more concrete example. I have a function named addup. We will add up to a certain number depending on what we pass in as an argument. The for loop within here will iterate once up to whatever number that n is, add I to sum, then return it. What if n was a large number like a million? Well, it's going to take just above a million steps to complete this function. This function is said to have a runtime complexity of O of n, linear time. As the amount of data increases, it's going to increase the amount of steps linearly or proportionally. Now, another way in which we could write the same function is to take sum equals n times n plus 1 divided by 2. We will get the exact same sum. So if n was, let's say, a million, this is still only going to take a couple steps, 3 steps, not a million steps. So this function is going to have a runtime complexity of O of 1. The input size doesn't matter. The amount of data that we have really doesn't matter. It's going to be completed in the same amount of steps. So this function is way better than this previous one. 3 steps is better than a million steps. And the reason that this isn't O of 3, because this takes 3 steps, is that we really don't care about smaller operations. In the grand scheme of things, they really won't make much of a difference. So we would just shorten this and say that this is O of 1 constant time. The input size doesn't matter. Here's a graph that I made to represent the different runtime complexities. We have data on the x-axis represented by n. So data will increase as we go more to the right, and we have time on the y-axis. I did add an asterisk next to time because some of these times can vary depending on what machine you're using, so these can vary. Another way to look at this is number of steps. So as we increase on the y-axis, these algorithms are going to perform with increasingly more time. They're going to get slower. So let's begin with O of 1 constant time. Anything that has a runtime complexity of O of 1 will take the same amount of time regardless of the data size. A few examples would include the random access of an element within an array and inserting at the beginning of a linked list. So O of 1 is extremely fast. Next, we have O of log n, also known as logarithmic time. One example is binary search. We haven't talked about this yet. We'll talk about a few of these algorithms in future videos. But anything that has a runtime complexity of O of log n will actually take, I don't want to say less and less time, but increasingly less time to complete. So as the data size increases, this algorithm is going to be more and more efficient compared to the early stages with a small data set. O of n is also known as linear time. As the amount of data increases, the time it takes to complete something will increase proportionally, linearly. That would include looping through the elements in an array and searching through a linked list. Next, we have O of n log n, also known as quasi-linear time. This would include quicksort, merge sort, and heap sort. We'll talk about these concepts in future videos. So for the most part, this is very similar to linear time, unless we're working with a large data set. Then anything using O of n log n is going to start to slow down when we work with larger data sets, hence this curve here. Then we have O of n squared, also known as quadratic time. A few examples would include insertion sort, selection sort, and bubble sort. As the amount of data increases, it's going to take increasingly more and more time to complete anything that has a runtime complexity of O of n squared. So just to compare linear time and quadratic time, with linear time, if our data set was 1,000, if n equals 1,000, it's going to take 1,000 steps. They're proportional, they're linear. But if we were using quadratic time, if n was 1,000, then 1,000 squared would be a million. So if our data set was 1,000, if we're using quadratic time, it's going to take a million steps then, way more than linear time. So quadratic time is extremely slow with large data sets, but in the case of a small data set, it could actually be faster, as you can see by the graph here. And lastly, we have O of n factorial, also known as factorial time, and one place where this is used is with the traveling salesman problem, which I might discuss in a future video. So this is extremely slow. So if I had to give a letter grade to each of these runtime complexities when working with large data sets with constant time, this would be an A, like an A+. Logarithmic time would be a B, it's pretty good. Linear time is C, it's okay. Quasi-linear time is a D, it's just barely passing. Quadratic time would be an F, and factorial time, well, you get expelled from school. Although some of these runtime complexities are actually faster when working with a smaller dataset, so keep that in mind. Well, that's the very basics of big O notation. It's notation used to describe the performance of an algorithm as the amount of data increases. So if you can, give this video a thumbs up, drop a random comment down below, and well, that's big O notation in computer science. All right, everybody, linear searches. We need to talk about linear searches because this wouldn't be a complete course without them. With a linear search, we iterate through a collection one element at a time. The runtime complexity of a linear search is big O of n. The larger the dataset, the number of steps to complete that search will increase proportionately. The disadvantages of a linear search is that they are slow for large datasets. But with the advantages, they are fast for searches of small to medium-sized datasets. And they don't need to be sorted. That's a huge benefit over binary searches and interpolation searches. And they are useful for data structures that do not have random access, such as linked lists. So let's begin. Let's create a basic array of integers. Int array. And to make up some numbers, they don't necessarily need to be in order. All right, then let's find an index. Int index equals, and we will invoke a linear search function, which we still need to declare. We will pass in our array and some value we would like to search for. Let's search for the number 1. Okay, so then let's declare this function. Create method, linear search, private static int, linear search. So we have two parameters, an integer array and an integer. I'm going to rename I as value, so it's more descriptive. Okay, with a linear search, all we need to do is loop through our array one element at a time. So we can do that with the for loop. So let's set int I, our index, equal to 0. We will continue this as long as I is less than our array's length, then increment I by 1. What we're checking with an if statement is to see if our array at index of I is equal to the value that we're searching for, this parameter. If it is, then let's return whatever our index is, I. If we do not find it after iterating through our entire array, let's return -1 as a sentinel value. And that's all there is to it to our linear search function. So back within our main function, let's check to see if the value returned does not equal -1. That means that we found our value. So with an if-else statement, let's check to see if index does not equal -1. That means that we have found our element. So let's print element found at index plus index. Else, let's print element not found. System.out.println, element not found. So if we're searching for the number 1, we would find that at index 1, 0, 1. If we search for 5, that is found at index 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. If there's some number that's not in here like 10, then this will print element not found. So yeah, that's the idea behind a linear search. We iterate through some collection one element at a time. It's slow for large datasets, but it's fast for small to medium datasets. This would be a small dataset, and they do not need to be sorted. That's a huge advantage. So yeah, everybody, that is a linear search. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, that is a basic linear search in computer science, I guess. Hey everyone, it's your bro, hope you're doing well, and in this video I'm going to explain the binary search algorithm in computer science. So sit back, relax, and enjoy the show. Alright, binary search. It's a search algorithm that finds the position of a target value within a sorted array or other collection. In order for a binary search to work, whatever we're searching through, it needs to be sorted. And basically what we do is we take half of the array and eliminate it during each step, and we will whittle down our collection until there is only one element remaining. In this example, I have an array of 11 elements. Each element contains a letter, and they're all sorted alphabetically. Let's say we are looking for the letter H and I need the index. What we would do with a binary search is that we always begin in the middle. We first check to see if our target value is equal to this middle value. If these are equal, then we can return this index. But odds are they're probably not going to be equal on the very first turn, the very first step. So these are not equal, then we will check to see if our target value is greater than or less than this middle value. Since H is greater than F, we can disregard this entire first half of our array, because since this is sorted, our target value could not possibly be within this first portion. and then we begin step 2, or phase 2. It's the same process as before. So again, we begin in the middle, check to see if our target value is equal to the middle value. They're not. Check to see if our target value is greater than or less than the middle value. This time h is less than I. We would delete the second half of this portion. We're not actually deleting these values, we're disregarding them. And then we can move on to step 3. We're repeating the same process as before. And this time, these elements divide evenly, so we would just round down and begin and say that this is the middle. So h is greater than g. We would disregard this element, and we only have h remaining, so we would return this index because these values are equal. And that's a binary search. Now, a binary search isn't too efficient when working with small data sets. However, if you're working with a large data set like 1 million elements, well, then a binary search is actually fantastic because we're eliminating half of the elements we are searching through during each phase or turn. So if we had 1 million elements after the first phase, we can already disregard like 500,000 elements, and then we just repeat the process until there's only one left. So if this was an iterative approach, we would need to search through these linearly, beginning with, index 0 and going all the way to 1 million. So a binary search is fantastic with large data sets. The runtime complexity of a binary search is O of log n. The larger the dataset, a binary search becomes more and more efficient compared to other search algorithms. Alright, let's perform a binary search in real life now. We'll use the built-in binary search method of arrays to begin with, and then later on we'll build our own binary search function. So we'll need an array to work with. Let's say we have an array of integers named array. Int array, and the size of this array will be 100. We'll increase the size later for demonstration purposes. And we'll need a target value that we're searching for. I'll just name this target. Int target equals, what about 42? We'll search for the number 42, and we'll need to populate our array. So we can do so using a for loop. Int I equals 0. We will continue this for loop as long as I is less than array.length, and increment I by 1 during each iteration. Then we will fill array at index I with whatever I is, our index. Okay, so the cheap way of using a binary search is to use the built-in binary search method of arrays. Let's say int index equals arrays dot binary search. And taking a look at this binary search method, there's 2 arguments that we have to pass in, an array and whatever we're searching for. So we will pass in our array and our target, then return the index. And let's display that. So let's check to see if our index is equal to -1. If our target is not found, then that means -1 will be returned from our binary search method. So let's print something. System.out.println. What about element not found? Actually, better yet, target not found. Let me change that. Target plus not found. Okay, then else. Else, we will display system.out.println element found at :space plus index. All right, let's try it. Okay, element found at 42. Cool. Now let's create our own binary search function for practice. I'll turn this line into a comment, copy it, paste it, and get rid of this erase portion. Okay, then I'm just going to use a shortcut to generate this function. Okay, so private static int binary search. There are 2 parameters, an array of integers named array, and int target. So we'll return -1. That acts as a sentinel value. -1 means that the value is not found. Now, what we'll need at this point is the beginning and ending index of our array. So let's say int low will be the beginning, and int high is the end. Array.length -1. So we have a low index and high index. And we'll create a while loop. While low is less than or equal to high, we'll continue this while loop and keep on searching through our array. So first we need the middle index. Int middle, and here's the formula for that. Low plus high minus low divided by 2. So we have our middle index. We will take int value equals our array at index of middle. So this will extract that value found within this element. Okay, so this portion is optional. I'm just going to display whatever this value is so we can count the amount of steps it's going to take to find a value. So let's say middle colon space, whatever this value is. This line of code is optional. I'm just doing this for educational purposes. Okay, now we need to check to see if our value is less than or greater than our target or equal to. If value is less than our target, low equals middle plus 1. And actually, I'm going to get rid of these curly braces. If you have an if statement and you only have like one line of code, you don't really need the curly braces. I'm just doing this so it's easier to read. Okay, else if value is greater than target, we will set our high index. High equals middle minus 1. Else, that means we have found our target. Else, return middle. So this means that target is found. And by returning -1, that means target not found. And that is our binary search function. Let's try it. Okay, element found at 42. So it took us, let's see, 1, 2, 3, 4. 4 steps to find the number 42 within this array of 100 elements. Now let's increase the size because binary searches do extremely well with large data sets. So let's say we have 1 million elements, and let's change this target. What about 777,000, whatever that number is? Okay, so let's search for it. And let's count the steps. So there's quite a number of steps here, but let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 steps. Now imagine if we took a linear approach where we began at index 0 and looped through this entire array looking for this index. And in that case, looping through an array would have a runtime complexity of O of n. To find this number, it's going to take over 700,000 steps because we're iterating once for each element within this array, compared to a binary search where it only took 20 steps. Well then, in conclusion, a binary search is a search algorithm that finds the position of a target value within a sorted array. Half of the array is eliminated during each step or phase. So that's a binary search algorithm. If you would like a copy of all this code, of course, I will post this to the comment section down below. And that is the binary search algorithm in computer science. All right, what's going on, everybody? Interpolation searches. These are an improvement over binary searches that are best used for uniformly distributed data. Basically speaking, we're going to make a guess, and I'm saying that within quotes. We're guessing where a value might be based on calculated probe results. If our probe is incorrect, our search area is narrowed, and a new probe is calculated. Basically, we're guessing where a value is going to be and return the index. So using an interpolation search, this has an average runtime complexity of big O of log n. And in a worst case scenario, where our values within our collection increase exponentially, this can have a runtime complexity of big O of n. So to demonstrate this, let's create an array of integers. Int array, we'll name this array, equals, and assign this some numbers all uniformly distributed. Let's say the numbers 1 through 9 all in order. This would be, I would say, a best case scenario. Then let's find an index. Int index equals, and we will invoke an interpolation search function. So interpolation search. We will pass in our array and a value we would like to search for. Let's search for the number maybe 8. Okay, then let's declare this function. Private static int interpolation search. There are 2 parameters, an array of integers and our value we are searching for. I'm going to rename this parameter as value so it's more descriptive. The first thing that we're going to do is calculate the upper bound and the lower bound of our searchable area. So int high will be the higher bound of our searchable area, and this will be our array's length minus 1. And the lower bound is, well, the first index. Int low, and I will set this equal to 0. Using a while loop, we will continue probing. The condition within our while loop is while our value is greater than or equal to our array at index of low, the lower bound, and our value is less than or equal to our array at index of higher bound. And our sizable search area is going to shrink after each iteration. So while our value is within the new searchable area, keep on probing, keep on searching. I'm going to add another condition too. Low is less than or equal to high. After each iteration, our searchable area is going to shrink. Once our searchable area is 0 elements, well, we can't search anymore, so we might as well exit. Now here's the formula to calculate where our value is probably going to be, and our guess will be referred to as our probe. Int probe equals, and here's the formula, high minus low times our value minus array at index of low, our lower bound, divided by array at index of high minus array at index of low. I'm just going to add low to the front of this, and I'm just going to make this a little bit more readable for us. Here's the formula to calculate where our value is likely going to be. It's a little complex to read this. A few of the contributing factors are the size of our current searchable area, high minus low. So to begin with, we have 9 elements times the value we're searching for minus the value at the lower bound, so 8 minus 1, divided by the value at the higher bound minus the array at the lower bound. Then at the end, we're just tacking on whatever our lower bound currently is. So it's a complex formula. All you have to do is just copy this. So during each iteration, I'm going to display our probe. This is going to be essentially our guess. And let's check to see if our probe is equal to our value. So using an if statement, let's check to see if array at index of probe is equal to our value that we're searching for. If it is, let's return our probe. This is the correct index. Else, if our guess, our probe, is incorrect, we'll need to narrow down our search area. So using an else if statement, let's check to see if array at index of probe is less than our value. If that's the case, we will need to set the new lower bound, low equals probe plus 1. Else, high equals probe minus 1. Now here's the deal with these statements. We're currently searching for the number 8. If we guess our probe is at, let's say, 5, and our value is greater than this probe, we can disregard this portion of the searchable area. So we're moving the new lower limit, the new lower bound, to just after where our probe was, 6. So this is the new searchable area. And then we'll calculate a new probe based on this data. If we're looking for, let's say, 2, and our probe says it's likely here at 5, well then, since 2 is less than our probe, we can disregard all of this data, and this would be our new searchable area. We would move the higher bound of our data down to just below our probe. So that's kind of the idea. So at the end, if we do not find our value, let's return -1 as a sentinel value. So back within our main function, let's check to see if the value returned does not equal -1. Using if-else statements, if index does not equal -1, then let's print a message. System.out.println, element found at index plus index. Else, element not found. Okay, so this should work. Let's run it. So we are searching for 8. So this formula calculated that this value is likely at probe 7, index 7, 0, 1, 2, 3, 4, 5, 6, 7. And this was the first iteration of our while loop. We were able to find our value 8 on the first iteration. So let's find a different value. How about 1? Element found at index 0. That's the first element. So interpolation searches work very well with uniformly distributed data. These numbers are all increasing by 1. So this is a little too easy for our interpolation search. it's guessing the likely index on the first try, so let's create a more difficult data set. So with our new data set, let's say that we will start with 1 and then double the number of the previous element. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. And let's search for the number, what about 256? Let's see how many probes this is going to take. All right, so here's the results. We iterated our while loop 5 times. We had 5 different guesses. After the first guess, this was not correct. So we narrowed down our search area, then we probed again. This still wasn't the correct answer, so we probed again, and again, and again, until we got the right value. So that's an interpolation search. It's an improvement over a binary search that is best used for uniformly distributed data. It guesses where a value might be based on a calculated probe result. If the probe is incorrect, the search area is narrowed, and a new probe is calculated. The interpolation search has an average runtime complexity of big O of log n, and a worst case runtime complexity of big O of n. This would be if our values increase exponentially. So yeah, that is the interpolation search. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, that is the interpolation search in computer science. Aw, yeah. All right, bubble sort. Bubble sort is a sorting algorithm that compares adjacent elements and checks to see if they're in order. If not, these elements are switched, then the next pair of adjacent elements is compared. And we continue on in that pattern until all elements are in order. While using bubble sort, I like to imagine that our collection is filled with water. Heavy things like rocks, sediment will sink to the bottom. Anything light, such as air, wood, bubbles, anything light will float to the top. Here's an array of 9 unordered elements. We will use bubble sort to manually sort these elements in ascending numeric order. Alright, so I reset this array. We're going to perform a total of 9 laps, but don't worry, I'll fast forward through this footage. So let's just walk through the first few steps. We will compare these first 2 adjacent elements. We'll check to see if the first element is greater than the second element. If it is, we will move this element to a variable, which will probably be named temp, short for temporary. Check the video in the Java playlist on how to swap variables. I think it's a pretty good video, but I might be biased with my opinion. We'll take the next element and place it where the first element was, then move this variable within temp into the spot that 1 was in, the previous element. Okay, so then we will check these next 2 adjacent elements. This first element is greater than the second element, so we will move our first element into temp, move the second element to where element 1 was, and then move temp to where element 2 is, and then we would just repeat this process. So we will lap through this array once for each element that is available. So let's just speed up the footage here, and I will show you manually a bubble sort. As you may have noticed, the bubble sort algorithm really isn't that efficient, even when working with smaller datasets. In most real-world applications, you'll probably use a different sorting algorithm, but this is still a good thing to learn. So the bubble sort algorithm has a runtime complexity of O of n squared. It runs in quadratic time. So the larger the dataset, the more and more inefficient that this sorting algorithm is going to be. With a small dataset, it's not horrible, but there's definitely better algorithms out there. So for practice, let's create our own bubble sort algorithm. Alright, let's create an array of integers and assign some random numbers. Make sure that they're not in order because, well, then that would defeat the purpose of this program. So at the end, we'll just display all the elements of this array using an enhanced for loop. For I in array, we will display with a print statement, not print line, whatever I is during each iteration. So let's just test this. So I have all the elements in my array printed, and they're currently not in order. So we'll need to declare a bubble sort method. Bubble sort, and then we will need to define this outside of our main method. So public static void, we're not returning anything, bubble sort, and then we will need to pass in an array. So that will be the argument array, and we will accept int array. Okay, so this is actually really easy to write, even though the bubble sort algorithm really isn't too efficient. So I guess that's one benefit. So we'll need nested for loops. And then the outer for loop will be int I equals 0. I is less than array.length minus 1 I plus plus. And let's do the same thing with the inner for loop, but we can copy what we have, change I to j. And this is going to be array length minus I minus 1. So we're going to check to see if array at index of j is greater than, that will be for ascending order, is greater than array at index of j plus 1. So that would be the next adjacent element. So if this number is greater than this one, we should switch these two elements around, and we'll need the assistance of a temporary variable. So let's declare int temp equals array at index of j. Then we will take array at index of j, set this equal to array at index of j plus 1, and then lastly we have array at index of j plus 1 equals whatever is stored within temp. And honestly, that's all there is to it. So this should sort our array, and it's in ascending order. So if you need this in descending order, we would just swap this greater than sign with a less than sign. And now this is in descending order. So even though the bubble sort algorithm really isn't too efficient, it's actually extraordinarily easy to write if you just need something really simple. So I guess that's one benefit. All right, everybody, that is the bubble sort algorithm. It compares pairs of adjacent elements and checks to see if they're in order. If they're not, they're swapped. And this process will repeat once for each element in an array or other collection. So this algorithm has a runtime complexity of O of n squared. So it's okay-ish for small data sets, and please do not use this for any large data sets. So if you would like a copy of this code, I will post this to the comment section down below. And well, that's the bubble sort algorithm in computer science. Hey everyone, it's me again, and in this video I'm going to explain the selection sort algorithm in computer science. As always, sit back, relax, and enjoy the show. Okay everybody, selection sort. Selection sort is an in-place comparison sorting algorithm that keeps track of the minimum value during each iteration, and at the end of each iteration, all we do is swap variables. How I like to imagine this is that let's say that our array is a bunch of different closed boxes, and each box contains a number, and they're all out of order. So what we'll do is we have a flashlight too, because we're in the attic and it's really dark. So we have a flashlight. We will open each box beginning with the beginning of our array, and we'll take a look at the value inside. Okay, 9 is a fairly small number, I guess, right? So we will move this value to some temporary storage. We'll keep track of the index of the minimum value. 9 is the new minimum. Let's open the next box, and holy crap, it's a 1. 1 is a really small number, so that will be the new minimum. Then we'll open the next box, which is an 8. 1 is still less than 8. Let's move on. The next box is 2, 7, 3, 6, 4, and 5. 1 was the minimum value during this iteration, and we need to move this value to the place that we started during this iteration, index 0. So we'll have to do some good old variable swapping. So we will take 9, place it within some temporary storage, then take 1 and place it where 9 was, then take 9 and place it where 1 was. And that is the first iteration. Let's move on to iteration 2, and we'll clear min and temp. Okay, so this portion is done now. We're not worried about it. This is the new beginning of the next iteration. And well, 9 is a low number, I guess. We'll move that to min. But 8 is even lower than 9, so we'll move that to min. Holy crap, it's a 2. 2 is the new min for sure. And then we just repeat this process over and over again. 2 is the current minimum of this iteration. 1 was the minimum of the first iteration, but we're not concerned with that. It's already sorted. So we need to move 2 to where we began this iteration at index 1. And currently there's a 9 in there, so we're going to evict this 9, place it within some temporary shelter, take 2, place it within where we started at index 1, then take 9, place it where 2 was. And that is the second iteration. Now that we kind of know how this process works, I'll speed up the rest of the video for this demonstration. So let's begin at index 2. And that is the selection sort algorithm. The selection sort algorithm has a runtime complexity of big O of n squared. The larger the dataset, the more and more inefficient that using the selection sort algorithm is going to be, although it's okay with smaller datasets. Now let's create our own selection sort algorithm. Okay, let's implement a selection sort. We'll need an array or other collection to work with. Let's create an array of integers because I want to make this as easy as possible. So integer, array, and make up some random numbers, make sure that they're not in order. What about 8, 7, 9, 2, 3, 1, 5, 4, 6, I guess. Then let's use a for each loop to iterate over the elements of this array. For int I in array, we will display each element with a print statement. System.out.print I. And let's run this once just to be sure that everything is working fine. So 879, 231, 546. Everything is working as it should. So before we display the elements of our array, let's invoke a selection sort function, which we still need to declare. So selection sort, and we will pass our array as an argument because, well, that's what we want to sort, right? So selection sort, and we'll need to create this method. I will cheat and use the shortcut. So outside of our main method, let's declare private static void selection sort. There is one parameter, an array of integers. We'll need a pair of nested loops to iterate over our array. So let's work on the outer loop. For int I equals 0, we will continue this as long as I is less than array's length property minus 1, then increment I by 1 during each iteration. Then there is a nested loop within here, change I to j. So j equals I plus 1, j is less than array length, and j++. So we'll need to keep track of the minimum, so we'll do that outside of our nested loop. Int min equals I. So that is the current minimum. And within the nested for loop, we will check to see if our array at index of min is greater than array at index of j. If it is, we will change our min to equal j. Then outside of our nested loop, but within the outer loop, we will do some good old variable swapping. So int temp equals array at index of I to store this element. Array at index of I equals array at index of min. Then lastly, array at index of min equals temp. And that's all there is to it. So after running this program, our array is now sorted via the selection sort algorithm. Then, of course, if you need your array or collection sorted in descending order, currently it's in ascending order, all we do is swap this greater than sign with a less than sign, and this will now be sorted in descending order depending on what you need. Well, okay then everybody, that is the selection sort algorithm. It will search through an array and keep track of the minimum value during each iteration. At the end of each iteration, we swap variables, and that's all there is to it. It runs in quadratic time, big O of n squared. It's okay with small datasets, even more so than bubble sort, and it's pretty terrible with large datasets. The larger the dataset, the more and more inefficient that this selection sort algorithm is going to be. So that is the selection sort algorithm. If you learned something new, give this video a big fat thumbs up. Drop a random comment down below, and well, that is the selection sort algorithm in, I guess, computer science. What's going on, people? It's bro, hope you're doing well, and in this video we're going to discuss the insertion sort algorithm in computer science. As always, sit back, relax, and well, enjoy the show. Alright everybody, insertion sort. Now what we do with insertion sort is that we begin at index 1. We take the value found within, move it to some temporary storage, like a variable named temp, to temporarily hold it. We examine elements to the left. If any elements are larger than what's within temp, we shift those elements to the right. So 6 is larger than 1, we shift it to the right. If it's less than whatever's within temp, we stop, or until we run out of elements. So we have run out of elements, we take this value found within temp, and place it at this opening here. That was the first iteration. Let's move on to iteration 2. Take this value, place it within temp, examine the elements to the left. If this element is greater than temp, then we shift it to the right. It's not, so we stop here and place this value back where it came from. So that was the second iteration. Iteration 3. Take this value, place it within temp, examine the elements to the left. If they're greater than 4, we shift them to the right. 7 is larger than 4, shift it to the right. 6 is larger than 4, shift it to the right. 1 is not larger than 4, so we stop here, take whatever's within temp, this value 4, and insert it here into this opening. So that was the first 3 iterations. We repeat this process until we run out of elements. So I'll speed up the footage. So we are currently on index 4. And that is your visual representation of the insertion sort algorithm. I like to think of it like a jigsaw puzzle. We have some pieces that are connected, they fit together, and we will move whole sections of pieces together to make room for a piece that fits. So let's create our own insertion sort algorithm in Java now. We'll need to create an array. Let's create an array of integers. Int array, and make up some numbers. Put whatever numbers you want within here. Maybe 9, how about a 1, and an 8, and a 2, and a 7, 3, 6, 5, 4. That sounds good to me. Okay, then let's display the elements of this array. We'll use a for each loop. For int I in array, we will display each element within this array with a print statement. So let me get rid of that print ln and just have print. So I will print I. I think I'm going to add a space afterwards. I didn't do that in the previous 2 videos, so I think I better do that. Okay, let's just run this just to test it. 918273654. And before we display the elements of our array, let's invoke a function which we still need to declare called insertion sort. So insertion sort. Then we will pass in our array as an argument. And we'll need to declare this. So I'm going to cheat and create this automatically. So outside of our main method, create a method named insertion sort. Private static void insertion sort. There is one parameter, an array of integers. Okay. Now the first thing we'll do is create a for loop to iterate over each element of our array, but it begins at 1, not 0. So that would be for, then we will set int I to equal 1, not 0. Pay attention to that. We will continue this as long as I is less than array.length, and we will increment I by 1 during each iteration. Now, we need to take our value found within I and place it within temp. So let's declare a temporary variable named temp. Int temp equals array at index of I. And now we'll create a variable named j. Int j equals I minus 1. So this will keep track of what value we're comparing to the left of whatever I is. So then we need to create a while loop. We will continue comparing values to the left of I. And our condition is going to be while j is greater than or equal to 0 and array at index of j is greater than temp. So if we need to shift an element to the right, we would say array at index of j plus 1 equals array at index of j. So that will shift an element to the right. Then we will decrement j by 1, j minus minus. And the last thing to do is to insert the value found within temp into that opening. So that would be array at index of j plus 1 equals temp. And that's all there is to it. So let's run this. Booyah! 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, people, in conclusion, the insertion sort algorithm compares elements to the left, and it will shift elements to the right to make room to insert a value. The insertion sort algorithm has a runtime complexity of big O of n squared. It runs in quadratic time. It's decent with small data sets, but bad with large data sets. And using insertion sort tends to be preferable to both bubble sort and selection sort. It uses less steps than bubble sort, and in the best case scenario, insertion sort can run in O of n linear time, compared to selection sort, which the best case scenario is O of n squared. Alright people, so that is the insertion sort algorithm. If you can, destroy that like button, leave a random comment down below, and well, yeah, that's the insertion sort algorithm in computer science. Well, howdy, y'all. We're talking about recursion. Now, recursion is when a thing is defined in terms of itself. I stole that definition from Wikipedia. Really doesn't make too much sense. A thing is defined in terms of itself. So basically, with recursion, we apply the result of a procedure to a procedure. A recursive method is one that calls itself, and this can be a substitute for iteration. There's a lot of overlap where you could use either recursion or iteration. With recursion, we divide a problem into subproblems of the same type as the original, and recursion tends to be used within advanced sorting algorithms and navigating trees. Some of the benefits of recursive code is that it's easier to read and write, and it's easier to debug. But the disadvantages is that it's sometimes slower and uses more memory. Let's begin with a very simple example. Let's create a method to simulate walking. We'll do this both iteratively and recursively, then take a look at the differences between the two. So let's write an iterative walk method. So we will need to invoke this method, and then we will pass in the amount of steps that we would like to walk, like 5 steps. And then we'll need to declare this method. Private static void walk, and I'll change I to maybe steps, just so that it's more descriptive. Now let's use an iterative approach. So iteration is the repetition of an internal process. So we can use a for loop. That will repeat a process. And let's say that int I equals 0. We will continue this as long as I is less than steps, and then let's increment I by 1 during each iteration. And then during each iteration, I will print you take a step. And really that's it. And after running this code, we have walked 5 steps. Now let's write the same method recursively. Recursion is the repetition of a procedure. Iteration is the repetition of a process. So with recursion, we need a base case. That's what we do when we would like to stop. And a recursive case, what do we do when we would like to continue? So our base case is going to be if steps is less than 1, then we will return. And if you only have one statement within your if statement, you don't really need these curly braces. So I'm just going to omit those. All right, then we will print you take a step. So this is our base case. This is what we do when we would like to stop. Then our recursive case is what we're going to do when we would like to continue. We will invoke the walk method within itself, but we will pass in steps -1. And this is our recursive case. And this will do the same thing, however, it's just written a little bit different. Now, one thing that you should know is that programs have a data structure called a call stack. A call stack keeps track of the order in which our program needs to function. So with the main method, we call the main method first, and that's added to the bottom of our call stack. So in order to complete our program, we have to complete the main method and get to the end of it. However, when we took an iterative approach, we invoked the walk method, and that was added to the top of our stack. Remember that video on stacks? It's a LIFO data structure, last in, first out. We have to take care of anything at the top of our stack first, and then work our way down. With a recursive approach, we're adding multiple frames onto our call stack, because 1, we're calling the main method, then we're calling the walk method, passing in 5 as an argument, then we're calling the walk method again, passing in 4 as an argument, then 3, then 2, then 1, then 0, then we return. And we have to solve this in a LIFO order, last in, first out. We begin at the top and remove frames from the top until we reach the end. So that's why using recursion is sometimes slower and uses more memory. We're adding more frames to the call stack. There's more methods that we have to keep track of. Now check this out. What if we take 1,000,000 recursive steps? We're going to call this walk method 1,000,000 times. And that's going to be a problem. And we ran into an exception. Let's take a look at this. So we encountered an exception, a stack overflow error. It's kind of like that one website. When working with recursion, it is possible to run out of memory. Although this is sometimes slower and uses more memory, recursive code tends to be easier to read and write and easier to debug. For a small method like this, I would probably stick with an iterative approach just because it already is fairly simple. But it's going to really come in handy when we get to topics on advanced sorting algorithms. So let's try something a little more complex. Let's create a program to find the factorial of a number. So let's create a factorial method, and we'll write this recursively. So let's find factorial, what about 7? And then we'll need to define this method. And we no longer need our walk method. So if we're taking a recursive approach, finding the factorial of a number, let's say that I is num. So we'll need a base case. If num is less than 1, we will return 1. This is our base case. Then we need a recursive case. We will return num times factorial, then pass in num minus 1. And then eventually we'll hit our base case because num is going to be 0. And this is our recursive case. Oh, then change void to int because I forgot. Okay, then let's display factorial 7 within a print line statement. Factorial 7. And the factorial of 7 is 5040. So you can see that this was fairly easy to write. It only took 2 lines of code. By the way, I found a great example of recursion on its Wikipedia page, and that's by the process of creating refreshed sourdough. So the recipe calls for some sourdough left over from the last time the same recipe was made. I thought that was a fairly descriptive example of recursion. Let's move on to level 3. Let's create a recursive method to find a base raised to a given power. Let's create a power method, and we need a base and an exponent. Let's find 2 to the power of 8, and then we'll need to define this method. Private static, let's change void to int, I to base, and j to exponent. We need a base case and a recursive case. The base case will be if exponent is less than 1, we will return 1. This is our base case. Our recursive case will be return base times invoke the power method, pass in base and exponent minus 1. And this is our recursive case. And then we will need to display the result. System.out.println 2 to the power of 8, which is 256. All right, everybody, so that's recursion. It's when a thing is defined in terms of itself. We apply the result of a procedure to a procedure, and a recursive method is one that calls itself. And this can be a substitute for iteration. We divide a problem into subproblems of the same type as the original, and recursion is commonly used within advanced sorting algorithms and navigating trees. Some of the advantages is that recursive code is easier to read and write and easier to debug. However, it's sometimes slower and uses more memory. So yeah, that is recursion. If you learned something new, be sure to smash that like button, leave a random comment down below, and well, yeah, that's recursion in computer science. Hey, what's going on, everybody? It's your bro, hope you're doing well, and in this video we're going to discuss the merge sort algorithm in computer science. So sit back, relax, and enjoy the show. Alright, what's going on, people? Merge sort. Merge sort is a divide and conquer algorithm. Basically what we do is that we will pass an array as an argument to a merge sort function. This function is going to divide our array in two. We have a left array and a right array. These will be subarrays, and we will copy the elements over from our original array to our 2 new subarrays. And merge sort is a recursive function, so at the end of merge sort, we will call merge sort again and pass in our subarrays that we create. And again, the merge sort function is going to divide our arrays in 2 by creating 2 new subarrays and then copy the elements over. And we will stop when our arrays only have a size of 1. And that's where sorting, then merging come in. And with the process of merging and sorting, we will create a second helper function named merge. Merge will accept a total of 3 arguments: our left subarray, our right subarray, and the original subarray in which these elements came from. Merge is going to take these elements and put them back into their original array in which they came from in order. And we will do the same thing with the next grouping of arrays until all of these elements are merged back into their original array in which they came from, all in order. Now, in practice, when we do execute this merge sort function, instead of tackling all of these subarrays like one layer at a time, we will tackle them by one branch at a time. So it's going to look a little something like this, where we will start with the leftmost branch and then work our way towards the right. So I'll speed up the footage and just give you a rundown of how this works in practice. And that, ladies and gentlemen, is the merge sort algorithm. The merge sort algorithm has a runtime complexity of big O of n log n. It runs in quasi-linear time, along with quicksort and heap sort, which we still need to talk about. So when working with large datasets, merge sort is faster than insertion sort, selection sort, and bubble sort. But on the other hand, the merge sort algorithm uses more space than bubble sort, selection sort, and insertion sort, because we need to create new subarrays to store elements, whereas bubble sort, selection sort, and insertion sort can sort in place, so they use a constant amount of space to do their sorting, unlike with merge sort. Now let's move on to the hands-on portion of this video and create a merge sort function in code now. Alright, well, let's get started. We'll need an array to work with, make up some numbers, make sure that they're not in order, as well as a for loop to iterate over the elements of our array. So currently our array is not in order, but that's going to change soon. Let's invoke a merge sort method that we still need to declare. This is going to be a recursive method, and we will pass in an array. And each time that we invoke this method, we will split our array in half, create two subarrays, and then copy the elements over. So let's create and declare this method. Private static void merge sort, and we'll need a helper method too. And we'll name this merge. A helper method is just a method that helps another method, basically. So private static void merge. And there's going to be 3 parameters within our merge method. Int left array, int right array, and int array. Remember that these are arrays of integers. The first thing that we're going to do within our merge sort method is that we need to get the length of our array. So let's cache that within a local variable named length. Int length equals array.length. And we'll need a base case too. When do we stop recursion? If length is less than or equal to 1, then we shall return. And this is our base case. Basically, with this merge sort method, we're dividing our array in 2 each time. If the length is 1, there's no longer a need to divide our array further. And we'll need to find the middle position of our array. Int middle equals length divided by 2. And we'll create 2 new subarrays. Int array left array equals new integer array, and the size is middle. And we'll create a right array. Integer array right array. The size is length minus middle. Okay, now we need to copy the elements of our original array to our left and right arrays. So we'll need 2 indices. Int I equals 0. This will be for our left array. And int j equals 0. And this is for our right array. Then let's create a for loop. We don't necessarily need to declare a new index here. We can just use I. So I'm going to add a semicolon. Our condition is I is less than length. Then increment I by 1 during each iteration. So our condition is, with an if statement, if I is less than middle, then we will copy an element from our original array to our left array. Left array at index of I equals array at index of I. Else, we will copy that element to our right array. Else, right array at index of j, remember that this index is for the right array, equals array at index of I. Then let's increment j by 1. Okay, this is where recursion comes in, so outside of this for loop, we will call merge sort again and pass in our left array. So we'll consistently divide our array in half. We'll begin by dividing the left array, then the right array, with a separate recursive call. So left array, then right array, and then call merge. So with merge, we have to pass in our left array, right array, and our original array, because we'll put the elements back in order. left array, right array, and our original array that we received as an argument. So that is it for the merge sort function. Let's work on merge next. First thing that we're going to do within the merge method is cache the size of our left array and right array within some local variables. Int left size equals array dot length divided by 2. Int right size equals array dot length minus left size. And then we'll need 3 indices. Int I equals 0. This is for our original array to keep track of the position. L will be in charge of our left array, and R will be in charge of our right array. And these will be the indices that we're using. Okay, the next part, we're going to check the conditions for merging. And we can do this with a while loop. So our condition is going to be while L is less than left size and R is less than right size. So basically, while there's elements within both our left array and right array, we will continue adding elements to our original array. And we'll need to check to see which element is smaller. If left array at index of L is less than right array at index of R, then we will copy the element from our left array to our original array. So we're basically comparing the number on the left to the right and adding whatever number is smaller back to our original array. So array at index of I equals left array at index of L. Then we can increment I, increment L. So if the number on the left is not smaller than the number on the right, we have to copy the element in our right array to our original array, and we can use an else statement. Else array at index of I equals right array at index of R. Increment I, increment R. So there's probably going to be one element remaining that we cannot compare to another element because there's only one left. So let's write a while loop for that condition. While L is less than left size, then we will take array at index of I equals left array at index of L. Increment I, increment L. Then we'll need another while loop. If R is less than right size, we will copy the last right element over. Array at index of I equals right array at index of R. Increment I, increment R. And that should be it. Let's run this. And our array is now sorted. In conclusion, everybody, the merge sort algorithm recursively divides an array in two, sorts them, and then recombines them. The merge sort algorithm has a runtime complexity of big O of n log n, and a space complexity of big O of n. So that is the merge sort algorithm. If you would like a copy of this code, I will post this to the comment section down below. And well, yeah, that is the merge sort algorithm in computer science. Hey, it's your bro, hope you're doing well, and in this video I'm going to explain the quicksort algorithm in computer science. Yep, so sit back, relax, and enjoy the show. Alright, quicksort. Here's how quicksort is going to work. We need an array or some other type of collection. I have a simple unordered array. What we do is that we'll pass our array as an argument into a quicksort function. After passing our array as an argument to the quicksort function, we need to pick a pivot. There's different variations of quicksort. We can either pick a pivot at the beginning, the middle, or at the end. But with most standard quicksort algorithms, we will set the pivot to be at the end of our array. What we're trying to accomplish is that we need to find the final resting place of our pivot. Where is this value going to be? And taking a look at this, That would be right about here. But we don't know that yet. So to find the final resting place of this value, our pivot, here's what we can do. We will declare and use two indices, j and I. J will begin at the start of our array. I will be one less than the beginning of our array, and that's going to be important later. And we'll need the help of a temporary variable so we can swap some values. All we're doing is checking to see if the value at j is less than our pivot. If it's greater than our pivot or equal to our pivot, we ignore it. 8 is greater than 5, we ignore this value, and then increment j by 1. So during that last iteration, I did not come into play yet, but it will this round. Again, we check to see if this value is less than our pivot, which it is. What we do now is increment I. Then what comes next is that we swap these two values, I and j, and we'll need the help of a temporary variable. So take the value at I, assign it to temp. Take the value at j, assign it to I. Take the value within temp, assign it to j. Then we can move on to the next iteration. Increment j. We check to see if the value at j is less than our pivot, which it is. If that is the case, we increment I, swap these two values. We'll repeat this process until j reaches our pivot. Then we can move on to the next step. Here's the next step after our index j reaches our pivot. We now know where the final resting place of our pivot is going to be. It's I incremented by 1. So we will increment I, then swap the value at index of I with the value at our pivot. Our pivot is now within the correct place. An easy way to tell is that all elements to the left of our pivot should be less than our pivot, but they're not necessarily going to be in order, and that's fine. They'll be organized later. All elements to the right of our pivot should be greater than or equal to our pivot. And like I said before, they probably will not be in order. The important thing is that elements to the left should be less than our pivot. Elements to the right should be greater than. That's how we know the pivot's in the correct place. Now the next step, we're going to create two sections, two partitions. The first partition will be all the elements from the beginning of our array up until our pivot, but not including the pivot. And our second partition will be all the elements after our pivot until the end of our array. Quicksort is a recursive algorithm. We need to pass these partitions as arguments into the quicksort function. Remember that the quicksort algorithm is a recursive divide and conquer algorithm. But unlike with merge sort we create new subarrays. With quicksort, we will be sorting these arrays in place, but we need to keep track of the beginning and ending indices of these partitions. And then it's just a matter of repeating the same steps over again, but we're going to instead use these partitions, sections of our array. I'll give you a quick demonstration of what the quicksort algorithm is going to look like to completion. And that, ladies and gentlemen, was your visual representation of the quicksort algorithm. Let's code our own quicksort algorithm just to solidify our understanding of this topic. Alright people, let's create a quicksort function. You'll need an array to work with, place some random numbers within that array, and then some way to iterate and display the elements of your array. I'm just using a simple for each loop. So after running this, of course, our array is not yet sorted. So before we display the elements of our array, let's invoke a quicksort function, which we still need to declare and define. There will be 3 arguments: our array, and the beginning and ending indices of our array. So that would be 0 for the beginning. Then to find the ending, you can just say array.length -1. Let's declare this function. Private static void quicksort. And let's rename some of these parameters. We have our array of integers named array, and this will be the starting index, and this parameter will be the ending index. So we have indices start and end. Now the base case, this will use recursion, will be if end is less than or equal to start, then we will return. And this is our base case. Eventually, we won't be able to divide our array any further, so that's when we stop and return. With our quicksort function, we'll need the assistance of a helper function that we will name partition. Let's copy our function declaration, paste it, and make a few changes. So this will return an int, the location of our pivot, and the function name will be partition, and the parameters are the same. At the end of our partition helper function, we'll return I. I will be the location of our pivot, but we'll get to that later. Okay, so within our quicksort function, we'll need to find the location of where to pivot. Int pivot, and the partition function will be in charge of that. Partition is going to sort our array and find the pivot. So all elements to the left will be smaller than our pivot. All elements to the right will be larger. So pass in our array. We're sorting our array in place. There's no need to create any subarrays. We'll just pass in our original array, as well as the start and end. After we figure out where our pivot's gonna be, we can pass in each partition recursively back into the quicksort function. So again, we will invoke quicksort, pass in our array, the start of our left partition, and the ending of our left partition, and that is where pivot is -1. We do not want to include our pivot, and then we will need to use quicksort on the right partition, change start to pivot +1, because the pivot is already in place, and then the end of our array. In this variation of the quicksort function, we will say that pivot is at the end. It will always be at the end to begin with. Int pivot equals array at index of end. We'll need 2 indices, I and j. We'll create index I equals start -1. And then we will iterate through our array. And this is where we will declare int j, our second index. Int j equals start. And we will continue this for loop as long as j is less than or equal to the end of our array -1. Then increment j by 1. What we're going to check is if array at index of j is less than our pivot. If one of these elements is less than our pivot, we want it on the left-hand side of our pivot. Any numbers larger than our pivot should be on the right-hand side. So we will increment I by 1 and do a basic variable swap. And we'll need the help of a temporary variable. Int temp equals array at index of I. Array at index of I equals array at index of j. Lastly, array at index of j equals temp. This is just a basic variable swap. Once all elements that are less than our pivot are on the left-hand side, and all elements that are larger than our pivot are on the right-hand side, what we will do now is increment I by 1, and then insert our pivot into its final resting place with another basic variable swap. So let's copy this code, then paste it, and make a few changes. Int temp equals array at index of I, that's the same. Array at index of I equals array at index of end. Array at index of end equals temp, and that's it. And then make sure you return I at the end. That is the location of our pivot. Then after running this, Our array is now sorted via the quicksort algorithm. In conclusion, the quicksort algorithm moves smaller elements to the left of a pivot. We recursively divide our array into two partitions and pass those partitions as arguments recursively into the quicksort function. The runtime complexity of the quicksort algorithm actually varies. In its best and average cases, it runs in big O of n log n. However, in its worst case, it can run in big O of n squared. This is rare, and it occurs if the array is already sorted or close to being sorted. But most of the time, it will run in big O of n log n. And the space complexity of the quicksort algorithm is big O of log n. This is due to recursion. It uses more space than bubble sort, selection sort, and insertion sort, even though it sorts in place. That's because the quicksort algorithm uses recursion. We're adding frames to the call stack, which takes memory. So yeah, that is the quicksort algorithm. If you found this video helpful, please be sure to smash that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Alright, what's going on everybody? Hash tables. A hash table is a collection of key value pairs. Each key value pair is known as an entry. We have two pieces of data. The first is the key, and the second is the value. In this example, let's pretend that we're a teacher and we need to create a hash table of all of our students. Each student has a name and a unique student ID number, but these can be of any data type that you would like. In this example, the key will be an integer and the value will be a string. So how do we know at which index to place each of these entries? Well, what we could do is take each key and insert it into a hashcode method. The hashcode method will take a key as input, plug it into a formula, and spit out an integer. This integer is known as a hash. Now, if we're finding the hashcode of an integer in Java, that's actually really easy. The formula is the number itself. So the hash of 100 is 100, 123 is 123, so on and so forth with the other keys. So after finding the hash of your key, now what can we do? These numbers are way too large, and the size of our hash table is only 10 elements. What we'll do next is take each of these hashes and divide each of them by the capacity, the size of our hash table. We have 10 elements. So take each hash, divide it by the capacity of our hash table. Whatever the remainder is, we will use the remainder as an index. And to find that, we will use the modulus operator. So 100 divides by 10 evenly. The remainder is 0. So 100 modulus 10 gives us a remainder of 0. So SpongeBob's entry we will place at index 0 within our hash table. So the hash of Patrick's key is 123. 123 modulus 10 gives us a remainder of 3. Patrick's entry will be inserted at index 3 of our hash table. So here's a little shortcut. If you have a number, modulus 10, you can find the remainder, and that is the last digit. 321 modulus 10 will give us a remainder of 1. Sandy's entry will be placed at index 1. Then Squidward's entry will be placed at index 5. 555 modulus 10 is 5. And Gary's will be at index 7 following the same pattern. Now here's one situation. What if two hashes are calculated to be the same value? That is known as a collision, and I can best demonstrate that with a separate example. In this next example, let's say that each key is now a string. Each entry is a pair of strings. We will first need to find the hash of each of these keys. So the hash code of a string uses a different formula. Basically speaking, we're going to take the ASCII value of each character within the string and plug it into this formula. I went ahead and calculated the hash of each of these strings using this formula of the string hashcode method. And the next steps are the same as before. Take each hash divided by the capacity of our hash table and find the remainder. So beginning with the first hash, 48,625 modulus 10, gives us a remainder of 5. SpongeBob's entry is now at index 5 within our hash table. Now Patrick's will be at index 0. Now here's Sandy's. Sandy's will also be 0. We have a collision. Both of these entries will be located at the same index. So what do? Each of these storage locations is also known as a bucket, and the most common resolution for a collision in a hash table is that we will turn each bucket into a linked list. If this bucket already has an entry, within the first entry, we will also add an address to the location of the next entry, and keep on adding more if there's more entries within this bucket. So in this way, this becomes a linked list. If we're looking up a key, we first go to the index in which it's located. If there's more than one entry, we will search linearly through this bucket as if it were a linked list until we find the key that we're looking for. So that's the most common resolution when there is a collision, but ideally you would want each of these entries to be within their own bucket. Based on the hash of Squidward's key, Squidward's entry has an index of 9, and Gary has an index of 5, and there's another collision. We will add the address of Gary's location to the first entry, and this bucket becomes a separate linked list. This process is known as chaining. The less collisions that there are, the more efficient that this hash table is going to look up a value. Ideally, you would want each entry to have their own bucket, but collisions are possible. To reduce the number of collisions, you can increase the size of the hash table. But then again, the hash table is going to use up more memory then, so people usually find a balance between the two. So yeah, those are hash tables in theory. Let's create our own now. Alright everybody, so let's implement a hash table in Java. So we will need to declare this hash table and list the data types of our key value pairs. If we need to store primitive data types, we can use the appropriate wrapper class. So let's store integers and strings. Integer and string. The integers will be the keys, the strings will be the values. We'll map student ID numbers and student names. And I'll name this hash table just simply table. Equals new hash table. There we go. So in Java, when we create a hash table, these have an initial capacity of 11 elements and a load factor of 0.75. So once 75% of our elements are filled, this hash table will dynamically expand to accommodate more elements. Now you can set a different capacity for your hash table. Instead of 11, let's say 10 to be consistent with our example in the previous part of this lesson. And if you would like to change the load factor, you can add that as well. Instead of 75%, let's say 50%, so we would pass in a floating point number. So 0.5, then add an F at the end for floating point numbers. But in this example, let's just keep the load factor consistent. So let's start adding some key value pairs. To add an element to your hash table, use the put method. So table.put, and then we will pass in an integer as the key and a string as the value. So our first student is SpongeBob. He has a student ID of, let's say 100. And let's pass in a string for the value, SpongeBob. Okay, that is our first student, so let's add a couple more from the previous example. So we have SpongeBob, Patrick with an ID of 123, Sandy with an ID of 321, Squidward with an ID of 555, and Gary with an ID of 777. Now to access one of these values, you can use the get method of tables. So I'll display this within a printline statement. Table.get, and I will pass in a key. Let's get the value at key number 100. So this student is SpongeBob. How can we display all of the key value pairs of a table? Well, we could use a for loop. So I'm going to create a for loop and place this within it. So to iterate over the keys of our table, this is what we can write. We can use an enhanced for loop. So we are iterating over integers. So the data type is integer, key, colon. So to make our hash table iterable, we can get all of the keys from our table and put them within a set. A set is iterable. So we will iterate over table.keySet method. This will take all of our keys and return a set. And a set is something we can iterate over. And within our printline statement, let's print each key plus, then maybe I'll add a tab to separate these, plus table.get, then pass in whatever our key is. Okay, so after running this will display all of our key value pairs. And if you need to remove an entry, well, there's a remove method. dot remove, then pass in a key. Let's remove Gary. So remove the entry with this key, 777, and Gary is no longer within our table. But we'll keep him in. I'll turn this line into a comment. Now, just to get a better understanding of where these key value pairs are being placed, let's also display each hash code for each of these elements. So preceding our key, let's display each hash code. I'll precede our key with a tab, and let's display each key's hash code, key.hashCode method. If we're using the hash code of integers, this will return the primitive integer value represented by the key that we're passing in. If we're using the hash code method of integers, well, the hash is going to end up being the same integer. So you can see that these numbers are the same. To calculate an index, we can follow the hash with modulus operator, then the size of our table. We set this to originally be 10. So we have Gary at index 7, Squidward at index 5, Patrick at 3, Sandy at 1, SpongeBob at 0. Now, if our data type was strings, we would use a different hashing formula. So let's change the data type to string, and all of these keys are now strings. Then let's remove modulus 10 and change the data type of our for loop to strings. String key. Okay, these are the new hashes for each of our keys. This key has this hash number, this key has this hash number, so on and so forth. So different data types will have different hash code formulas. Now let's calculate the element in which each of these entries is going to be placed by adding modulus, the size of our hash table, 10. So here are the elements, and we actually have two collisions. We have a collision with these two keys. They're both within bucket 5, as well as these two entries. So both of these will be placed into bucket 0. Since there's more than one entry within the same element, we will treat this bucket as a linked list and just iterate over it linearly until we reach the key that we're looking for. Now, one way in which we can avoid collisions is to increase the size of our hash table. If we set this to the default of 11 and change this to modulus 11, well then these will be placed within different buckets, and you can see that they changed. However, we still have a collision with SpongeBob and Squidward. So what if we increase this to 21? Do we have any collisions then? Nope, we do not. These keys are within their own buckets. Alright everybody, so in conclusion, a hash table is a data structure that stores unique keys to values. When you declare a hash table, you state the data types of what you're storing, and these are reference data types. Each key value pair is known as an entry, and a benefit of hash tables is that they have fast insertion, lookup, and deletion of key value pairs. But they're not ideal for small data sets, since there's a lot of overhead, but they're great with large data sets. Hashing in the context of a hash table takes a key and computes an integer. It utilizes a formula which will vary based on the key as input and its data type. Then to calculate an index, we follow this formula. We take a hash, modulus, the capacity of our table to calculate an index. Each index is also known as a bucket. It's an indexed storage location for one or more entries. They can store more than one entry in the case of a collision, and in case that happens, we treat each bucket as a linked list. Each entry knows where the next entry is located. And as we discussed, a collision is when a hash function generates the same index for more than one key. Less collisions equals more efficiency. And the runtime complexity of a hash table varies. If there are no collisions, the best case would be a runtime complexity of big O of 1. It runs in constant time. In case there are exclusively collisions, as in we place all of our entries within the same bucket, it's going to be one giant linked list. And the runtime complexity of a linked list is big O of n. It runs in linear time. On average, the runtime complexity of a hash table will be somewhere within this range. So yeah, everybody, those are hash tables. If you would like a copy of all my notes here, I'll post them in the comments section down below. And well, yeah, those are hash tables in computer science. Alright, what's going on everybody? Graphs. A graph is a nonlinear aggregation of nodes and edges. A node, also known as a vertex, may contain some piece of data, and an edge is a connection between two nodes. There are two types of graphs we're going to discuss, undirected and directed. An example of an undirected graph could be a social network like Facebook. Each node could represent a user, and if one user is friends with another user, well, we could establish a friendship, an edge, a connection between these two nodes. If two nodes are connected, they have what is known as adjacency. In this example, Larry is friends with Patrick and Sandy, so Larry has adjacency to Patrick and Sandy. Patrick is friends with Larry, Sandy, SpongeBob, and SpongeBob is friends with Sandy, Patrick, and Squidward. And Squidward is adjacent to only one neighbor, SpongeBob. So a social network could be an example of an undirected graph. The other type of graph is a directed graph. A directed graph contains edges that will link one node to another. However, these are one-way connections. In this example, node A would have adjacency to node B, but not the other way around. However, it is valid to have one node pointing to another node, and that node could point back to the previous node. An example of a directed graph could be a street map. Let's say you're working on a travel app, and each node is a possible destination. These single edges could be one-way streets, and these double edges could be two-way streets. You can move back and forth between these two destinations. There are two popular ways to represent a graph, an adjacency matrix and an adjacency list. With an adjacency matrix, we could create a 2D array or 2D array list, one row and one column for each node. If we need to check to see if there's adjacency between two nodes, we would first find the index of the node we're beginning at, let's say A. So we would go to node A, and then find the index of the node we're trying to travel to, so B. So row A, column B. If there are no edges, this would be 0. If there is an edge, this would be 1. So since there's 1 here, within row A, column B, well, there's adjacency from node A to node B. But if we take a look at row A, column C, this is 0, so there's no adjacency between A to C. But if there was, well, we would replace this 0 with 1 then. Now there are pros and cons with the matrix. One of the benefits is that the runtime complexity to locate an edge is big O of 1, it's constant. All we have to do is find two indices. So we have to find the row and the column. However, the space complexity to store a matrix is big O of v squared. V as in the number of vertices that we have. But you could also think of that as n for the number of nodes. Big O of n squared. So since we have 5 nodes and 5 columns, we would have a total of 25 spaces. So the benefits of a matrix is that it's very quick to look up an edge. However, a matrix uses a lot of room, so it tends to suit graphs that have a lot of edges. On the other hand, we have an adjacency list. An adjacency list is an array or array list of linked lists. Each element is a separate linked list, and each header within the linked list would contain the address of a node. If there's adjacency between one node and another, we would add the adjacent node to our linked list. So to find adjacency between two nodes, we would find the node that we're starting at. Let's see if B is adjacent to E. So we would locate index B and travel this linked list until we find the node that we're looking for. That means there is adjacency between nodes B and E. Even if there's a node that is not adjacent to any neighbors, we would still want to add it to our adjacency list, just in case we do update it. Here are the pros and cons of an adjacency list. The time complexity to locate an element is big O of v. V as in the number of vertices. You can also think of this as n, so this would be big O of n. To locate an edge, we would first access the node that we're beginning at by an index. So let's begin at B, and we are looking for adjacency between B and E. Since each element is a linked list, we need to traverse this linked list linearly until we find the node that we're looking for. So in that way, it's linear. However, a benefit of a list over a matrix is that they use less space. The space complexity of an adjacency list is big O of v plus E. V for the number of vertices, aka nodes, and E for the number of edges. So yeah, everybody, those are graphs. A graph can be used to model a network. Each node is a piece of data within our network, and an edge connects nodes. So like I said, it's a popular way to model networks, which don't necessarily have any sort of order. So yeah, that's an intro to graphs, and in the next two topics, we'll create our own adjacency matrix and adjacency list. Hey, if you enjoyed this video, give it a thumbs up. If you have any ideas of where else you could implement a graph, let me know in the comment section. And of course, subscribe if you'd like to become a fellow bro. Hey everybody, it's your bro, hope you're doing well, and in this video I'm going to show you one way in which we can create an adjacency matrix in computer science. So sit back, relax, and enjoy the show. Alright people, so an adjacency matrix. An adjacency matrix is a 2D array to store ones and zeros to represent edges between nodes. There are different variations. You could use booleans, so you could say true or false depending if there's an edge or not. And basically the number of rows and columns in an adjacency matrix is equal to the number of unique nodes. The runtime complexity to check an edge is big O of 1, it's constant, and the space complexity is big O of v squared, so it uses up a lot of space. Now let's create our own adjacency matrix. They're actually fairly simple. So I'm going to create two classes, graph and node. So file, new, class, I will name this graph, finish, file, new, class, and I will name this class node. So let's say that each node has some data, maybe a single character, char data, and I'll create a constructor. Node will pass in some data when we create a node. Char data, this dot data equals data. Within the graph class, I'm going to declare a 2D array of integers. So integer 2D array, and I will name this matrix. And within the graph constructor, we will instantiate our matrix. Matrix equals new int. Now we need to declare a size of this matrix. When we construct a graph object, let's set up a parameter. So int size. Size will be the amount of nodes that we have. And the size of this 2D array will be size and size. That's why the space complexity is big O of v squared. It's the number of vertices squared. If we have 5 nodes, well then the size is going to be a total of 25 elements. Now let's declare a few methods. Public void add node. And then we will pass in a node, node, and add edge. Public void add edge. Then we need two indices, a source and a destination. Int source, int destination, DST for short. We'll need a method to check an edge. Public, and this will return a Boolean value. Boolean check edge. And we'll need a source and a destination for parameters. And let's create a print method. Void print. Okay, we'll fill in add a node a little bit later. So let's fill in add edge. We will pass in a source and a destination, two indices. So source will be the row, destination will be the column. So what we're going to do is take our matrix at index of source and destination and set whatever value is in here, which will be 0, equal to 1. That means there's an edge between two nodes. And that's really it. Within the check edge method, we're going to check within our matrix if a given value is equal to 1. If it is, return true. If not, return false. So using an if statement, let's check to see if matrix at index of source and destination is equal to 1. That means there's an edge. If there is an edge, let's return true. Else, we will return false. And that's it. Okay, now before we actually print our graph, let's actually create a graph. So let's get rid of this. Graph equals new graph. And we can add some nodes, although this method doesn't do anything quite yet, but it will in the future. And we need to pass in a size, so let's pass in 5. We'll create 5 nodes. So to add a node, type graph.add node, and this is a method that we created. And I will pass in an anonymous node, or you can use a named one. So we have new node, and then to create a node, we need to pass in some data because that's what we decided on. So let's pass in the letter A. So this will be node A, and we'll create a few more nodes. B, C, D, and E. And we also can add edges between these nodes to represent adjacency. So to add an edge, type graph.add edge. So what we're doing in this example, think of each node as having an index number. To create an edge between two nodes, we will pass in the index number of each node. If I need an edge between nodes A and B, well, each of these has an index number within our matrix. So this first node would have an index of 0, and the second node would have an index of 1. If I need an edge between these two, I will add edge between 0 and 1. And let's create a few others. So how about B and C? So C would have an index of 2, and C will have 2 edges based on the previous video. So C will be connected to D, so 2 to 3, as well as E, so 2 and 4. D won't have any edges. This is a directed graph in this example, and E has 2 edges. We have E to A, that would be 4 to 0, and E to C, 4 and 2. Now let's print our graph. Graph.print, and we need to fill in this method. Within the print method of the graph class, we just have to print our 2D array, and we can use for loops for that. So this will be the outer for loop, int I equals 0. We will continue this as long as I is less than the length of our matrix, matrix.length, then increment I by 1. So this will iterate over all of the rows in our matrix, and then we need a nested for loop. So change I to j within the nested loop. Whatever index we're on, we will take matrix at index of I dot length this time as the stopping condition. And during each iteration of the inner for loop, I will use a print statement, and I will print matrix at indices of I and j. Then I'll add a space between each of these. Oh, then when you exit the inner for loop, let's print a new line. Okay, and here's our adjacency matrix. Each row corresponds to a node, as well as each column. If there's adjacency between 2 nodes, well then there will be a 1 at that row and column. This next part really isn't necessary. This is kind of the general idea of an adjacency matrix, but let's add some headers to the rows and columns. Within the graph class at the top, let's create an array list. Array list, and the data type will be node, and I will name this nodes. When we construct a graph object, let's instantiate our nodes array list. Nodes equals new array list. And when we add a node, we just take our nodes array list dot add node. And within the print method, let's make a few changes. So preceding our nested for loops, let's print the data found within each node. So it serves as a header. And I can use a for each loop for this. For every node in nodes, then let's print the node's data. Then maybe I'll add a space. Oh, then add a new line. Okay, there we go. Each column has the data found within each node. And let's also do the same thing with each of these rows. I think it would look cool. Before the inner for loop, let's do the same thing. Let's copy this line. But this would be nodes.get index of I.data. And let's see how that looks so far. Okay, not too bad, but let's add a few spaces. So system.out.print, and I'll just print 2 spaces. All right, there's our adjacency matrix. If you're working with more complex data, let's say city names, I would consider using printf statements instead because you can align things properly. And if you do want to check an edge, we did create a check edge method. So within a print line statement, let's invoke the graph.checkEdge method and then pass in 2 indices. So let's see if there's an edge between nodes A and B. So A has an index of 0, B has an index of 1. There is an edge between these two, so this will return true. There is an edge. This time, let's check to see if there's an edge between D and C. So D has an index of 0, 1, 2, 3. And C has an index of 2. And this returns false. There is no edge. All right, people, so that's an adjacency matrix. It's an array to store ones and zeros to represent edges. The number of rows and number of columns is equal to the number of unique nodes. The runtime complexity to check an edge is big O of 1. All we need are 2 indices. However, the space complexity for an adjacency matrix is big O of v squared. Take the number of nodes you have and square it. So if I have 5 nodes, 5 squared is 25. We have 25 elements. All right, so that's an adjacency matrix. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, that's an adjacency matrix in computer science. Hey, what's going on everybody? It's your bro, hope you're doing well, and in this video I'm going to explain adjacency lists in computer science. So sit back, relax, and enjoy the show. Alright, what's going on everybody? Adjacency lists. An adjacency list is an array or an array list made up of linked lists. Each element is a separate linked list, and each linked list can contain nodes. And each linked list has a unique node at the head. And basically speaking, to represent a graph, all adjacent neighbors to a node are added to that node's linked list. If we add an edge, we just add the address of that node to the tail. So let's begin. Let's create two classes, graph and node. File, new class. This will be graph. Finish. Then file, new class, node. Let's say we have some data, maybe just a single character. Char data. And we'll create a constructor, and then pass in some data. Char data. This dot data equals data. Within our graph class, we need to create an array list of linked lists. Array, list, and the data type of what's going to be stored are linked lists. Now we need a data type for our linked lists. What are the linked lists going to store? Well, they're going to store nodes. Let's name this array list just a list for adjacency list. And let's create a graph constructor. And we will instantiate our adjacency list. A list equals new array list. Okay, let's declare some methods. We'll need an add node method. So public void add node. And there is one parameter, a node of the node data type. We'll need to add an edge. Public void add edge. We'll need two indices, a source and a destination. Int source, int destination. We'll be able to check an edge. Public void check edge. Again, we'll need source and destination indices. And let's print our graph. Public void print. Alright, now let's head to our main class and instantiate our graph. Graph equals new graph. We're going to reuse a lot of the same code from the previous topic on adjacency matrices. So let's add some nodes. Graph.add node. And I will pass in an anonymous node. New node. And we need some data. So let's pass in the letter A. Let's copy this and create 4 additional nodes. So B, C, D, and E. And we need to create some edges. Again, I'm using the edges from the previous topic. So graph.addEdge. Each of these nodes has an index number. The first will be 0, the second will be 1, then 2, 3, 4. If I need an edge between nodes A and B, the index of node A is 0, that's the source, and the destination is B. That has an index of 1. So 0, 1. And let's fill in a few others. How about 1 and 2, 1 and 4, 2, 3, 2, 4, 4, 0, and 4, 2. Okay, so then at the end, let's print our graph, but we have not yet filled in the methods. So graph.print. Okay, so let's head to our graph class and fill in some of these methods. Let's begin with add node. So in order to add a node, we first need to create a new linked list. So linked list, the data type of this linked list is nodes. And let's name this current list equals new linked list. After we create this new linked list, we can add a node to the linked list. Current list dot add node. Whenever we create a new node, we will also create a new linked list, and the new node will be at the head of the linked list. And lastly, we just need to add this linked list to our array list. A list dot add current list. Okay, then let's fill in the add edge method. I will declare a linked list, and I'll just copy this. Linked list current list equals, to add an edge to our adjacency list, we first need to get a linked list from the array list. So let's store that within current list. Current list equals, to access our adjacency list, we will type a list dot get, and then an index, and that will be source. This will return a linked list. It's kind of like it's in two layers. We'll also need to know our destination node. So let's say node, destination node, equals, then we'll need to find the array list that this node is located at the head. Adjacency list dot get our destination index, then follow this with get 0. That is the head of our linked list. So this is the address of the node we would like to link to. And now we just need to add this node to the tail of our current list. Current list dot add destination node. And that's it. We're taking a node and adding it to the tail of a linked list. You can shorten this code if you would like to do so in less steps. You would just take this portion and replace current list with alist.getSource. Then you technically don't need this line, but it's a little more difficult to read, so you do you. Okay, this time let's check an edge. So we can copy these two lines of code, paste it. What we're going to do is iterate over our current linked list and see if there's a match between a node and our destination node. So let's use a for each loop, and we will iterate over all of the nodes within our current linked list. So the data type is node in our current list. With an if statement, let's check to see if the current node that we're looking at is equal to our destination node. Are these addresses the same? If so, then return true. If we escape the for loop, that means we did not find the node we were looking for, so let's return false. And the return type of this method is going to be Boolean. Okay, we have one more method. We just need to print our adjacency list. We'll use nested for each loops. So we need to iterate over all of the linked lists within our array list. So for linked list, the data type is node, and let's name this current list. Iterate over every linked list in our array list, and then we'll need another for each loop. For every node in current list. Then let's use a print statement. Print the node's data. Then maybe I'll add an arrow for flavor to represent a linked list. Then outside of our inner for loop, let's print a new line. And that should be everything that we need, so let's run this. Alright, so there is our adjacency list. Basically, an adjacency list is an array or an array list made up of linked lists. Each linked list has a unique node at the head, and all adjacent neighbors to that node are added to the node's linked list at the tail. The runtime complexity to check an edge is big O of v, v for the number of vertices. It's because we need to traverse a linked list linearly to find a matching node. And the space complexity for an adjacency list is big O of v plus e. V as in the number of vertices, e as in the number of edges. So yeah, that's an adjacency list. It's an array or an array list made up of linked lists. It's used to represent a graph. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, those are adjacency lists in computer science. Alright everybody, depth first search. Depth first search is a search algorithm for traversing a tree or graph data structure. We can break this down into 3 steps. When navigating a graph, we will pick a route, and we will keep on going until we reach a dead end or a previously visited node. If we do, then we will move on to step 3. We will backtrack to the last node that has unvisited adjacent neighbors. Let's navigate this maze using a depth first search approach. Here's the entrance, and here's the exit. So the general concept of a depth first search is that when we reach more than one adjacent neighbor, we're just going to pick a route. Let's say we prefer right turns over left turns, but you can really set any rule that you want. When faced with more than one adjacent neighbor, I'm just going to pick a route and keep on going. And if we reach a dead end, then we're just going to backtrack to a node that has some unvisited adjacent neighbors. So there's no more place we can go, so we're going to backtrack all the way back to this intersection right here. This route is unvisited, so we will continue going. Not backtracking yet, there's no dead ends, but now there is, so we backtrack and keep on going. So this is what this looks like sped up. And we have reached the end. Let's use a depth-first search approach to navigate this graph. Maybe we're at node A, and we need to travel to I, but we don't know where I is. One way in which we can keep track of our position is to use a stack, or in the case of recursion, we can use a call stack. Whenever we visit a node, we will push it onto the stack. We can either travel to nodes B or D. So we will mark D as visited and push this node onto the stack. Then we can either go to E or G. Let's go to G. We'll push that onto the stack. Then H, E, and now we circled around back to D, but D is already marked as visited, so we're going to backtrack to a node that has unvisited adjacent neighbors, which is A. So we will pop all of these nodes off of the stack all the way back to A, which has unvisited adjacent neighbors, and this time we will go down this route and push all of these nodes onto our stack. And we have reached the end. Using a depth-first search approach, when simplified, you pick a route, you keep going. When you reach a dead end or a node you already visited, you backtrack to a node that has unvisited adjacent neighbors, and you repeat steps 1 through 2. Alright, well, let's implement this in code now. And here we are, people. So I'm going to be using a graph that utilizes an adjacency matrix. If you're using an adjacency list, the code's just going to be a little bit different, but the concept is really still the same. I'm using code from the previous few videos. We have a node class, a graph class, and in the previous videos, we've already populated this graph with nodes and edges. And then I'm just going to print this. This is my adjacency matrix. Now within the graph class, we're going to create a depth-first search method and a helper method. So this will be public void, and we will name this depth-first search. And there will be one parameter, an index of where we would like to begin. To keep track of the nodes that we've already visited, what some people like to do is that they will create a boolean within their node class, such as boolean visited, and they'll just mark it as false or true. However, it's very easy to forget to change these back to false when you exit the depth-first search. So what I'm going to do instead is create an array of booleans, and the size will be equal to the length of the matrix. So let's create a boolean array, and I will name this visited equals new boolean, and the size of our array is the length of our matrix. Then lastly, we will implement a helper function. So let's name this DFS helper, and we will pass in our source and our boolean array visited. Then we just need to create this method, private void DFS helper, and there are two parameters, int source and an array of booleans named visited. You can either implement a depth-first search iteratively using a stack, or you can utilize the call stack if you use recursion. In this example, we're going to use recursion. When we invoke this helper function, we're going to check to see if the current node that we're on is visited or not, and we can use an if statement. If our visited array at index of source is equal to true, or you could write the shorthand and just say if visited at index of source, since this returns a boolean value. If we've already visited this node, we're going to return, else we will mark this node as visited. Else visited at index of source equals true. If you would like, although this part's not necessary, within my console, I'm just going to print that we visited this node. So within a printline statement, I do have my nodes within an array list. I'm just going to access the data of one of these. Nodes.get source.data plus equals visited. This part technically isn't necessary, but it's going to help with my demonstration. In this example, maybe we start at node A. We need to find any adjacent neighbors. If we're using an adjacency matrix, we need to iterate over this row. We can use a for loop for that. So int I equals 0. We will continue this as long as I is less than our matrix at index of source dot length. This equals the length of a row, and then increment I by 1. We're checking to see if one of these elements is a 1. That means that's an adjacent neighbor that we can travel to using an if statement. If matrix at indices of source and I. Source is the row that we're working with, I is the column. If this is equal to 1, then we will invoke the DFS helper method again. So this is recursive. We will pass in I as well as our Boolean array named visited. If we successfully search through an entire row outside of the for loop, let's return. And that's it. So let's run this. Within my main class, I will call the graphs depth first search method and pass in an index of a starting node. So let's begin at 0. We visit A first, then B, C, D, E. Let's try B, which has an index of 1. B, C, D, E, A. C, which has an index of 2. C, D, E, A, B. Okay, now pay attention to this. This is a directed graph, and we're beginning at D. There's no place that we can go, so we're stuck at D. We only visit D. And lastly, we have E, which has an index of 4. E, A, B, C, D. All right, everybody, that is the depth first search algorithm. You pick a route, you keep going. If you reach a dead end or an already visited node, you backtrack to a previous node with unvisited adjacent neighbors. If you would like a copy of this code, I'll post this to the comment section down below. Don't forget to give this video a thumbs up, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Alright, what's going on, people? Breadth first search. Breadth first search is a search algorithm for traversing a tree or graph data structure. This is done one level at a time, rather than one branch at a time, like what you see with depth first search. Here's an example. In the previous topic on depth first search, we would navigate a graph one branch at a time. But in a breadth first search approach, we would navigate this graph one level at a time. So let's begin at node A, and we are attempting to travel to node I. Instead of a stack, we'll use a queue. All unvisited nodes we will add to the queue. So we're currently at A, we'll add that to the queue, then add any unvisited adjacent neighbors to the queue as well. We have both B and D as neighbors. So we will add these to the queue, then add any unvisited adjacent neighbors of nodes B and D. That means we will add C, E, and G. And for the next level, we have F and H. And lastly, I. So that is a breadth first search approach. We will navigate a graph one level at a time using a queue, rather than one branch at a time using a stack, like with depth first search. Let's implement this in code now. Okay, everyone. So in my graph, I'm utilizing an adjacency matrix. We're reusing the same code from the previous few videos, and we have a node class that contains some data. And I went ahead and populated this graph already. It's the same data from the previous few topics. Heading to our graph class, let's create a breadth first search method. Public void breadth first search. And we will take an integer named source. This will be the index of the node we would like to begin searching at. And with a breadth first search, we can utilize a queue. So queue, we will store integers. These will be indices. And I will name this queue equals new. Now, queues are actually interfaces. We need to use a data structure that utilizes the queue interface, one of which is a linked list. Okay, so we have our queue, and we're going to create an array of booleans to mark if a node has been visited or not. So let's create a boolean array named visited equals new boolean, and the size will be matrix.length. With the node that we'll begin at, let's add that to the queue. Queue dot, you can use add or offer. And then pass in the index of the starting node. Then within the Boolean array of visited, we will mark this as true. At index of source equals true. And now we'll need a while loop. Our condition is that we'll continue this while loop while the queue's size method does not equal 0. We'll assign our source equal to whatever is at the front of the queue. Queue.pull to remove an element. With this code that I've written, I've already went ahead and created an array list of the nodes to access the data. Whenever we pull a node, I'm going to display the data. So this part technically isn't necessary. Nodes.getSource.data plus equals visited. Let's say that we're at node A. We're going to iterate over this row and look for any adjacent neighbors. So let's use a for loop for that. For int I equals 0. We will continue this as long as I is less than our matrix at index of source dot length. This means the length of the row, then I plus plus. During each iteration, let's check to see if this value is 1 and the node that we're trying to visit has not already been visited. If, then matrix at indices of source and I is equal to 1, and visited at index of I is not true, so we can use the not logical operator. If we have an adjacent neighbor that's not been visited, then we will add the index to the queue, and that node is going to wait in line. Queue dot offer I, and I is an index. And then mark this node as visited, so take our Boolean array visited at index of I, set this equal to true, and there we go. Let's invoke the breadth first search of our graph class, then pass in an index of a node we would like to begin at. In this example, node A has an index of 0, B is 1, C is 2, so on and so forth. So let's perform a breadth first search beginning at node A. We will cover these nodes in this order: A, B, C, E, D. Let's change this to 1. That would be node B. B, C, E, D, A. 2 is C. C, D, E, A, B. 3 is D. We can't go anywhere from node D, so only D is visited. And E. E, A, C, B, D. Now, before we wrap things up, here are the differences between breadth and depth first searches. Breadth traverses a graph level by level. Depth traverses a graph branch by branch. Breadth utilizes a queue. Depth utilizes a stack. Breadth tends to be better if the destination is on average close to the start, and depth tends to be better if the destination is on average far from the start. In a breadth first search, siblings are visited before children. In a depth first search, children are visited before siblings. And if you ever plan on creating video games, depth first searches tend to be more popular than breadth first searches. Alright everybody, that is the breadth first search. If you would like a copy of this code, I'll post this to the comment section down below. Don't be afraid to give this video a thumbs up, drop a random comment down below, and subscribe if you'd like to become a fellow bro. Alright everybody, here's a quick introduction to trees. In this video, we're only going to cover some of the terminology. A tree is a nonlinear data structure where nodes are organized in a hierarchy. This could be one example of a tree. It's made up of nodes and edges. Nodes could be some piece of data, and edges represent a relationship between two nodes. A real-life example of a tree could be a family tree. Maybe we're at node D, that's us, or me, or you. B is a parent, E is your brother or sister, A is a grandparent, C could be an aunt or uncle, and F is your cousin. A few examples of where a tree data structure would be used in programming or technology would be file explorers, databases, domain name servers, and the HTML document object model. The top of the tree is known as the root node. The root node doesn't have any incoming edges, only outgoing edges. Any nodes at the bottom of a tree are known as leaf nodes. They do not have any outgoing edges, but they do have incoming edges. And branch nodes are in the middle. They have incoming and outgoing edges. Here's a few other terms. Any nodes with outgoing edges are also known as parents. Any node with an incoming edge is known as a child node. And nodes can be both parents and children, if they have both incoming and outgoing nodes. Any two children that share the same parent are known as siblings. Nodes D and E both share the same parent of B, so D and E are both siblings. The same thing goes with B and C. Nodes B and C share A as a parent, so these two nodes are siblings. It's just like a family tree. A subtree is a smaller tree held within a larger tree. You could say that this portion is a subtree. The size of a tree is equal to the number of nodes. So what's the size of this tree? We have 1 node, 2, 3, 4, 5, 6. The size of this tree is 6. 6 nodes. The depth of a node is the number of edges below the root node. Our root node would have a depth of 0. Then as we move down levels, B and C have a depth of 1, D, E, and F have a depth of 2. And lastly, the height of a node is the number of edges above the furthest leaf node. All of these leaf nodes are the same distance away from the root node. These would all have a height of 0. B and C have a height of 1, and A has a height of 2. Well, alright then everybody, that is a quick introduction to some of the terminology around trees. It's a nonlinear data structure where nodes are organized in a hierarchy. And in the next few topics, we'll get a little more in depth with trees. If you found this video helpful, please help me out by smashing that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Alright, what's going on everybody? In this video, we're going to discuss binary search trees. But first, we'll need to know what a binary tree is. A binary tree is a tree where each node has no more than 2 children. That's why it's binary. In this example, node 1 has 2 children, 2 and 3, and each of these children have their own children. They have no more than 2 children. Nodes 4 and 5 are the children of 2, and nodes 6 and 7 are the children of 3. In this similar example, this would also be a binary tree. Node 3 only has 1 child, node 6. But with a binary tree, no node has more than 2 children. Since node 3 has 1 child, that's fine. But if node 3 had 3 children, well, that would no longer be a binary tree. Now, what makes a binary search tree different from a binary tree is that the values are arranged in a certain order. Here's the order. The root node should be greater than the left child, but less than the right child. 4 is greater than 2, and 4 is less than 6. That's the pattern that this data structure is built around. If we take a look at some of the subtrees, let's say this one, 2 is greater than 1, but less than 3. And in this subtree, 6 is greater than 5, but less than 7. If done correctly, starting at the root node, the leftmost child should be the least value, and again, starting from the root node, the rightmost child should be the greatest value. The reason that these nodes are arranged this way is for quick lookup. Let's say we're looking for 5. What we'll do is compare 5 to the root node. If 5 is equal to the root node, well then we found our answer. If 5 is greater than our root node, we will move down to the right branch and do the same thing again. Is 5 equal to 6? No, it's not. However, it's less than 6, so we know to go down this branch. The runtime complexity to find a value within a binary search tree is big O of log n in its best case. So let's code a binary search tree now. Okay, let's begin. Let's create a node class, file, new class. I will name this node, and finish. Nodes will have some data, maybe an integer this time, int data, and the node class should contain at most 2 nodes. Node left for the left child, and node right for the right child. If a node is a leaf node, well then these will be null, but we would still like to allocate space to hold children. And within the constructor, we will pass in some data, int data, and assign it. This dot data equals data. Now let's create a binary search tree class. File, new, class, binary search tree. And within our main class, let's instantiate a binary search tree object. Binary search tree, I'll name this tree, equals new binary search tree. And within the binary search tree class, each binary search tree should have a root node. Node root. Here are some methods. We'll need an insert method to insert nodes. Public void insert. And there is a parameter of a node. Node node. Now let's create a second method. This next method will be a helper method of the insert method. So the insert method is going to call its helper method. And this will be private. The return type is node. Insert helper. We need a root node. Node root. And a node. Node node. In order for our program to compile, we do need to return something, so just as a placeholder, I'm going to return null. Okay, for the next method, we need a display method. Public void display. and a helper method, private void display helper. And this has one parameter, a root node, node root. Next method is a search method, public boolean, we're returning a boolean, search, and the parameter is int data. And we will need a helper method, private boolean search helper. There are two parameters, node root and int data. Again, we do need to return something. I'm going to return false just as a placeholder. Okay, next method is a remove method, public void remove, and the parameter is int data, and we'll need a helper method. The return type is node remove helper. The two parameters are node root and int data. We do have to return something, so as a placeholder, I'm going to return null. Our remove helper method is also going to rely on two separate methods, one to find a successor and another to find a predecessor. This is in case we're deleting nodes, we have to shift nodes around. So this will be private int successor, and we will pass in node root. And we need to return something. Let's return 0 as a placeholder. And let's copy this, paste it, and this will be method predecessor. And that will be it. So let's close these for now and begin with the insert method. So with the insert method, we will assign our root node equal to insert helper method, pass in our root node, and node. So the reason that we're using helper methods is that we'll be using recursion. So it's a lot easier to use recursion if you have a helper method. Within the insert helper method, let's declare int data equals our node's data. Node is the node that we're passing in to insert. So let's check to see if our root node is assigned or not. So if our root is equal to null, then we should probably assign this node to the root node because, well, this is the first node. Root equals node. Return root. If root is not null, we have to compare the data to see if it's less than our root or greater than our root. Else if our data is less than the data of the root node, then we are going to assign this node as the left child of our root node. Our root's left child, root.left, equals, and we will use recursion, insert helper method. Pass in our root's left node and our node. The root node is going to change with recursion. At first, it's going to be the root node of the entire tree. After recursion, we're examining the root node of a subtree. So if we're passing in the left child of the original root node, well then, that left child is now the root node of a subtree that we're currently working with. So else if the data is less than the current root node, we go left. If it's greater than the root node, then we will go right. Else, root.right, that's the right child, equals insert helper method, pass in root.right, and our node. And it's the same process all over again. And at the end, we will return the current root node. Okay, that is it for the insert method and the insert helper method. So let's insert a few nodes, although we can't yet display them. Let's insert some anonymous nodes. Tree.insert, and we can pass in a node, either a node name or an anonymous node. So let's pass in some anonymous nodes. Let's pass in the number 5, or some other number of your choosing. And let's pass in a bunch of numbers. How about 1 and 9? Make sure these are not in order. 7 and 3, 6, 4, and maybe one more. 8. If you run and compile this, there is nothing obvious that really happens. So let's work on a display method next. So with the display method, we will invoke our helper method. Display helper, pass in the root node. Within the display helper method, we're going to check to see if the root node of our subtree does not equal null. So if root does not equal null. If you would like to display these in order, we can use in order traversal, and that uses recursion. So invoke the display helper method, pass in the root child's left node, root.left. If we're using recursion, the first piece of data that's displayed is the least value, and these values will be displayed in increasing order. Technically, the term is non-decreasing, but think of it as ascending order. So the very first value is going to be the least one, followed by the root node of this subtree. System.out.println root.data. In our first subtree, the data all the way to the left is 1, and the root node of that subtree is 2. Then we need the right child, which should theoretically be 3. So again, we'll invoke the display helper method and pass in the right child. So this is in order traversal. All of the nodes will be displayed in non-decreasing order. So let's try this. At the end of our main class, let's invoke tree.display and see what happens. Yeah, there we go. All of the nodes within our binary search tree are now in order. If you would like this in reverse order, you can just change these methods around. Replace left with right and right with left. And these are now in decreasing order. But let's change that back. Okay, up next we have the search methods. Okay, search will return, then invoke the search helper method. Pass in our root node, as well as some data. Within the search helper class, we'll check to see if root is equal to null. That means our tree is empty. So of course we can't search for anything. Return false. Then add else if our root.data is equal to data. That means we found the data that we're looking for. There's a match. Then we're going to return true. We found what we're looking for. Else if our root's data is greater than our current data that we're looking for. That means we need to go left. So return, then invoke the search helper method, pass in the left child, root.left. And the left child is now the root node of this subtree. And then you need to pass in data as well. Else, we go right. So copy this, paste it. Return search helper root.right and data. And we can get rid of this return statement at the bottom. Okay, let's try this. So at the end of my main class, let's use a print line statement, and I will type tree.search, and let's search for 0. None of my nodes have 0 as a piece of data, so this should return false. Let's search for 1 now. That returns true. There's a 1 within one of my nodes. What about 9? That is also true. And let's try 10. And that is false. Okay, so those are the search methods. And lastly, we have the remove methods, as well as successor and predecessor. Now, these methods are going to be a little bit tough, but I'll try my best to explain it. So within an if statement, let's check to see if this data even exists first. So let's invoke the search method and pass in our data. So this returns a Boolean, true or false. If we do find the data that we're looking for, then let's invoke the remove helper method. Pass in our root node as well as our data. Then within an else statement, and this part's optional, let's let the user know that we can't find that data. Data plus could not be found. So just to test things real quick, I'm going to remove some data that doesn't exist. Tree.remove 0. 0 cannot be found. Now let's move on to the remove helper method. The first thing that we'll do is check to see if our root node is equal to null. If our root node is equal to null, Then let's return the root node. Then within an else if statement, let's check to see if the data that we're trying to remove is less than the data of our root node. If it is, we need to go left down the binary tree. Root.left equals, then invoke the remove helper method. Pass in the left child of the root node, root.left, as well as our data. So we're going to go as far left as we can. Then add an else if statement. Else if data is greater than the data of the root node, then we will go right. So let's copy this, paste it. Root.right equals remove helper, pass in root.right, as well as our data. Then add an else statement. If we reach the else statement, that means that we have found our node, and I'll just add a note to explain that. If the node we're trying to remove has children, that kind of complicates things, then we have to shift the nodes around. But first, let's check to see if it's a leaf node, then that's really easy. Within an if statement, we will check to see if the left child is equal to null and the right child is also equal to null. That means that the node that we're trying to remove is a leaf node, and that's really simple. We don't need to shift any nodes around. We can just set this current root node equal to null. However, if the node we're attempting to delete has a right child, we'll have to shift those nodes around and find a successor. Else if root.right does not equal null, that means there's a right child, and we need to find a successor to replace this node. So we will assign root.data is equal to the successor method, which will find a successor for us, and pass in the current root node. Then take root.right equals and invoke the remove helper method, pass in the right child, root.right, as well as root.data. So when we delete a node, that will create a gap. And if there's a child, well, we don't want that child to be lost. We don't want that child to become an orphan. So we will link a child to that spot where we deleted a node. Now, if there's a left child, we have a slightly similar procedure. So we can use an else statement. Take root.data and invoke the predecessor method. Take this line of code, paste it, root.left equals remove helper method, pass in the left child of the root node. This else statement will find a predecessor to replace this node. And at the end, we will return root. So we can close out of these two methods, and we can open up the successor and predecessor methods. What we're doing with the successor method is that we're attempting to find the least value below the right child of this root node. We will assign the current root node equal to root.right. Then within a while loop, we will take root.left and check to see if it is not equal to null. While this condition is true, take root, set this equal to root.left. And at the end, return root.data. So what's happening here within the remove helper method, if the node we're trying to delete has a right child, we need to find a successor to fill in that gap. And that successor should have the least value. So we will go right and look as far left as we can, because values on the left are less than the root. Numbers on the right are greater than our root. After going right, we will go as far left as we can to get the lowest value, then return it. So that's what we're doing when we're assigning a successor to fill in that gap when we delete a node that has children. And then the predecessor method is going to be very similar. We will find the greatest value below the left child of this root node. So we can copy all of this, paste it. This time we will go left, then go as far right as we can go. I do apologize, this is a lot to take in. Recursion can be very confusing. But yeah, that's everything. Let's attempt to remove a node. So before we display our tree, let's take tree.remove. then pass in the data of a node you would like to remove. Let's remove 1. And here are the remaining nodes. We have 2 through 9 all in order. Let's remove 5. Okay, 1, 2, 3, 4, 6, 7, 8, 9. Let's remove 9. 9 is no longer there. And let's remove a node that is not within here, like 0. 0 cannot be found. Alright then everybody, that is a binary search tree. Just so you're aware, the order in which you insert nodes into a binary search tree does matter if it's unbalanced. Technically, my tree follows all the rules, however, it's fairly lopsided. There is a way to balance binary trees, but that's a topic for AVL trees. That's why the runtime complexity has a best case scenario of big O of log n, but a worst case scenario of big O of n, depending on how balanced it is. But basically, a binary search tree is a tree data structure where each node is greater than its left child, but less than its right. The benefit of a binary search tree is that it's easy to locate a node when they are in order. So yeah, those are binary search trees. If you would like a copy of this code, I'll post this to the comment section down below. Don't be afraid to smash that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Hey everybody, so let's talk about tree traversal. Tree traversal is the process of visiting all of the nodes of a tree. We don't have random access, so we begin at the root node and follow a certain procedure to visit all of the nodes of a tree. And there's 3 that we're going to talk about: in order, post order, and pre-order traversal. In this example, we will be working with a binary tree, not a binary search tree, because these values are not in binary search tree order. So each node has at most 2 children, a left node and a right node. Let's begin with an in-order traversal. Here's a recursive method that will navigate a tree in order. Using recursion, we visit as many left nodes as we can, followed by the root node, and then any right nodes. The entry point is always the root, and using recursion, we will go as far left as we can. So we go from A to B to D. So we will mark this node as visited, then visit the root node next, and then the right node. Since we can't go left anymore, we're going to visit the root node, A. All that's left is to go right, so we will go to C. However, we can go left, so we will visit F first, then C, then G. So this is in-order traversal. When used in the context of a binary search tree, we will visit all of these nodes in non-decreasing order. So again, that was D, B, E, A, F, C, G. We go left, root, right. And here's that method again. And here's post-order traversal. It's used to delete a tree from leaf to root. And we follow this pattern: left, right, root. We will use recursion to visit the left children, then the right children, then the root. So A is our entry point. We are going as far left as we can. Go from A to B to D. Mark D as visited. Then we go right using recursion. Go from D to E, then root. Left, right, root. So we go back up, go as far right as we can unless we encounter a left child, which we did. So we will mark F as visited, then G, right, root. Left, right, root. And all that's left is the root node. So that is post-order traversal. It's used to delete a tree from leaf to root. And lastly, we have pre-order traversal. Pre-order traversal is used to create a copy of a tree. We visit any root nodes first, then left, then right. So we will mark A as visited, our entry point, then visit the left child, and we will continue to go left, then go right. So we can't go left anymore, we're going to go right, mark the root as visited, then left, then right. This is used to create a copy of a tree. But in order to create a copy of a tree, you need to create a root node and a branch node to hold the leaves. So again, that's root, left, we're still going left, right, root, left, right. A, B, D, E, C, F, G. That is pre-order traversal. It's used to create a copy of a tree. Well, okay then everybody, that is a few ways in which we can traverse a tree. Like I said, normally we don't have random access, so the entry point is the root node, And you can either follow an in-order, post-order, or pre-order traversal, depending on what you need to do with this tree. So that's tree traversal and computer science. If you liked this video, please be sure to give it a thumbs up, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Hey everybody, in this video I thought I would show you all how you can get the runtime of a program. I thought it might be useful now that we know how data structures and algorithms work for the most part. So within the entry point of your program, you'll need the start time. And we'll store this within a long data type. I'll name this start equals, then type system.nanotime. A nanosecond is a billionth of a second. And then we have our program, whatever it is. And then at the end of our program, we will get the duration. This will be of the long data type. Duration equals, and then we need the current time, system.nanotime, minus our start time. This returns a time in nanoseconds. If you need milliseconds, you can divide this number by 1 million. Okay, then let's print the duration. System.out.println, duration plus milliseconds, or some other unit to measure time. Okay, so with our program, let's just have the main thread sleep for maybe 3 seconds. Whatever it is you want to do. And we will sleep for 3,000 milliseconds. And here we go. So we will wait for 3 seconds, and we are done. This program took 3,014 milliseconds to complete. When you enter your program, get the start time. At the end of your program, get the current time minus the start time. Then depending on the units you're using, you may need to divide this number by 1 million, or if you need this in seconds, you would divide this by 1 billion. So yeah, that's how to calculate the runtime of a program. If you found this video helpful, please be sure to smash that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro. Hey you. Yeah, I'm talking to you. If you learned something new, then help me help you in 3 easy steps by smashing that like button, drop a comment down below, and subscribe if you'd like to become a fellow bro.